Hey everyone! Welcome to our exciting course on building practical mobile AI apps using TensorFlow. Throughout this journey, you'll gain hands-on skills in creating powerful machine learning models that can be deployed on both iOS and Android. We'll cover essential concepts like RNNs, GANs, and even dive into building interactive applications with engaging coding exercises along the way. Plus, there's a GitHub repository linked in the description where you can access all the code we'll be working with. Make sure to stick around until the end because there's a final project waiting for you to really test your new skills. So, without further ado, let's dive in and get started. Let's dive into the exciting world of retraining with Mobilenet models. In recent years, Mobilenets have gained a lot of attention for their lightweight architecture and impressive performance on mobile devices. So, today, we'll explore how to effectively retrain these models using TensorFlow, and I'll show you how you can implement it in your Android or iOS applications. It's a fascinating topic, especially considering the capabilities these models bring to portable devices. So, let's get started. First up, we'll look at what Mobilenets are and why they're so popular in mobile computing. Then, we'll jump into the steps for retraining these models. Don't worry if you're not a TensorFlow expert yet. I'll guide you through the process, and you'll find that it's pretty straightforward. Once we get our model retrained, I'll also touch on how to integrate it into your mobile apps. So whether you're on Android or iOS, you'll be well equipped. Just imagine how powerful it'll be to leverage these models for image classification or object detection right on your phone. So grab your favorite coding environment and let's get retraining with Mobilenets. It's going to be a fun ride. Mobilenet is designed with efficient on-device machine learning in mind. Unlike traditional models like Inception v3, which can be over 200 MB in size, Mobilenets are much more compact. They usually range from a few MB up to, say, 17 MB for larger configurations. Now, this reduction in size doesn't compromise performance significantly. Mobilenets still manage to achieve decent accuracy, all while requiring fewer operations. This makes them perfect for mobile applications, particularly when resources are limited. The efficiency is gained through something called depth-wise separable convolutions, which break down the filtering process into two simpler operations, depth-wise and point-wise convolutions. To begin retraining with Mobilenet, the first thing you want to do is set up your environment. Ensure you've got TensorFlow installed, along with any other tools needed for your mobile development setup. Once you have that sorted out, the next step is to choose the specific configuration of the Mobilenet model you want to work with. You can select from a variety of configurations depending on your needs. The architecture parameter can be set to one of the following values: Mobilenet _1.0 _224, Mobilenet _0.75 _224, Mobilenet _0.50 _224, or Mobilenet _0.25 _224. Each of these configurations represents a different balance between accuracy and model size. Now, let's implement the command that will help us retrain your Mobilenet model using TensorFlow. This command kicks off the retraining process by calling the retrain.py script, which is tailor-made to adapt a pre-trained Mobilenet model for your specific image classification task. Now, the -output graph flag is super important because it defines where the retrained model will be saved for later use. In this instance, we're directing it to a .pb file located in your TF files directory. Similarly, you'll need to set up the -output labels flag. This one shows where to save the label file that corresponds to your new classes. And trust me, you're going to need this file later to help interpret what your model predicts. Next, don't forget the -imageder argument. This points to the folder that holds your training images, which is key for the model to learn all about the features of the new classes we are introducing. Then we have the -bottleneckder option. This is where those intermediate representations of your images will be stashed away, and it's quite handy because it really speeds up the retraining process. Finally, there's the -architecture parameter, which lets you choose which version of Mobilenet you want to work with. For this example, we're going with Mobilenet at a width multiplier of 1.0 and an input size of 224. So, by customizing these parameters, you can finely tune the retraining process to get the best performance possible for your unique application. When you run this command, TensorFlow will kick off the retraining process utilizing the images from the directory you specified. Now, it's crucial to keep in mind that the label file generated will mirror the structure and nomenclature you'd see with larger models like Inception v3. In short, you're just swapping out the backbone architecture while keeping the operational workflow intact. Now, let's discuss something important during the retraining phase. Have you thought about utilizing quantization? When you add _quantize to your architecture, like Mobilenet _1.0_224_quantized, you end up with a quantized model which significantly reduces its size. For instance, a quantized Mobilenet typically weighs in around 5.1 megabytes, compared to the non-quantized version that's about 17 megabytes. This size reduction can be a game changer for mobile applications, where speed and performance are key factors. Now, let's explore how we can implement the label image utility to classify new images using our retrained Mobilenet model. First, we need to specify the path to our retrained graph. This step is crucial because it contains the structure and weights of our model. Next up, we'll indicate the image file that we want to classify. For our example, this image is located at /tmp/lab1.jpg. All right, so we've got the image sorted. Now we need to define the input and output layers of the model. The input layer is set to input, which is where we'll feed our image data into the model. And for the predictions, the output layer is designated as final result, which typically reflects the probabilities for each class. It's essential to tie this back to what we expect the model to do. Additionally, we should specify the path to the labels file generated during the retraining process. This file maps class indices to human-readable labels, which is key for correctly interpreting the model's predictions. Finally, let's set the dimensions for our input image to 224 by 224 and apply normalization parameters like input mean and standard deviation. These aspects help align our image data with the format the model expects. This setup is really vital for achieving accurate classification and allows label image to effectively process and predict the content of the image. Now, let's take a look at the output format that TensorFlow generates when classifying an image using our retrained Mobilenet model. When you run the label image utility, it provides predictions in a structured format. This format includes both the class label and its corresponding probability. For instance, you might see an entry like N0209971 Labrador Retriever 41, 0.8246. This indicates that the model predicts the image is most likely representing a Labrador Retriever with a confidence level of about 82.5%. Now, this probability really reflects the model's certainty about its classification, allowing you to assess how confident it is in its predictions. Additionally, for the same classification task, you may also encounter predictions for other classes. You might see something like N0209960 Golden Retriever 64, 0.14425, and perhaps N021040029 CUVAS 76 colon 0.10353. These show lower probabilities for these alternate classifications. Understanding these outputs is crucial because they inform you not just of the dominant predicted class, but also give insight into the model's relative confidence across various categories. And let me tell you, this information is invaluable for applications focused on image recognition, like pet photography or even animal identification in videos. Next, we're going to write the command to build the benchmark model tool, which lets us evaluate the performance of our trained models. This command uses Bazel, a build tool that's really handy for compiling large code bases. The -c opt flag here, that specifies we want an optimized build, and that's super important for performance benchmarking, especially in resource-constrained environments like mobile devices. Now, let's dive into the benchmarking process. Once we build the model, we can run it against our retrained models to measure their efficiency in terms of floating point operations per second, or flops. The command will specify the graph file of our retrained Mobilenet model as the input, along with crucial parameters like the input layer and its shape. Here's a pro tip. Setting the -show summary flag to true allows us to receive a detailed output of the model's performance metrics. This is essential for assessing how many computations the model needs during inference. All of this is critical when making informed decisions about model deployment, especially when comparing models like Mobilenet and Inception v3. It really reveals the trade-offs between speed and accuracy in real-time applications. So, whether you're building a mobile app that can identify dog breeds or creating a smart camera that recognizes different objects, retraining with Mobilenet gives you the flexibility and efficiency you need for modern development. As you dive into this exciting journey, don't forget to iterate on your model, test different configurations, and, of course, have some fun with it. Machine learning isn't just about crunching algorithms, it's about enhancing user experiences with intelligent technologies. In the end, retraining models is a crucial skill in today's AI landscape. With tools like TensorFlow and Mobilenet, you've got everything right at your fingertips to make fantastic advancements in mobile AI solutions. So roll up those sleeves, get your code ready, and let's make some magic happen in your mobile applications. In the ever-evolving landscape of mobile AI applications, developers often face a crucial decision: which model to use for their needs. Specifically, when should we opt for Inception v3 or Mobilenet retrained models on mobile devices? In this discussion, we're going to explore the performance comparison between these two models, dive into their strengths and weaknesses, and provide some real-world coding examples. This will help you make informed decisions regarding your mobile AI projects. So far, we've learned about the retraining process of Mobilenet models, focusing on their lightweight architecture and efficiency for mobile applications. We've gone through setting up the environment, selecting model configurations, and executing retraining with the retrain.py script in TensorFlow. We've also covered the importance of testing those retrained models using the label image utility. And let's not forget, we discussed the performance advantages of Mobilenet compared to traditional models like Inception v3. Now, here's where it gets really interesting. We'll delve into a comparative study of Inception v3 and Mobilenet models, looking closely at performance, accuracy, and efficiency. Let's get started. To start with, let's dive into how these two models stack up against each other. So, Inception v3, this is a widely used deep learning model, right? It's known for its high accuracy, but here's the catch: it comes with a hefty computational price. Now, when we compare that to Mobilenet, which was specifically designed for mobile and edge devices, we see that Inception v3 requires a lot more processing power and memory. If your application really prioritizes high accuracy, especially in tasks like image classification, then Inception v3 might be your go-to model. But be prepared for some longer inference times and a more substantial memory footprint. Just to give you some context, Inception v3 needs around 11.42 billion floating point operations, or flops, to perform a single inference. For a smartphone like the iPhone 6, which can handle about 2 billion flops, that means running this model could take around 5 to 6 seconds. And let's be honest, that's not optimal for mobile users, right? On the flip side, we have Mobilenet. This one is all about efficiency. It strikes a balance between speed and accuracy. With its lightweight architecture, Mobilenet significantly reduces computation without losing too much accuracy. For instance, during benchmark tests, a typical Mobilenet model only requires about 1.14 billion flops to do an inference. That results in inference times that are roughly 10 times faster than what you'd get from Inception v3. So, there you have it, two models with very different strengths depending on what you'll prioritize in your application. Now, let's take a look at how we can retrain a Mobilenet model for image classification using TensorFlow. First, we kick off the retraining process by running a command that points to the retrain script included in the TensorFlow examples. Now, here's something important. The underscore output graph parameter defines where the newly trained model will be saved. This is super convenient because we can easily use it later for inference. For our example, we'll store the model as dog_retrained_mobilenet102224.pb. Next up, we have the underscore output labels parameter, which saves the corresponding labels for our retrained model. This step is crucial for understanding the classifications that our model will deliver. Now, let's move to the underscore imagedir parameter. This tells the retraining script where to find the images we're using for training. It's really important to make sure that these images are relevant to the classes we want to identify. Don't overlook this part. Next, we include the underscore bottleneckdir parameter, which is the location for storing the bottleneck feature data. And trust me, this helps speed up the retraining process significantly. Lastly, we use the underscore architecture flag to choose the specific Mobilenet configuration. In this example, we opted for Mobilenet 1.0.224. This architecture is lightweight and optimized for mobile use, which makes it an ideal choice for efficient deployment. There you have it, a comprehensive overview of retraining a Mobilenet model. Now, let's dive into testing the performance of our retrained Mobilenet model using the label image utility. This utility is crucial for validating how well our model performs on images it hasn't seen before. We'll run a command that outlines the location of our trained model graph, the input image, and the necessary processing parameters. So, the command begins with the path to the label image executable, followed by the flag -graph, which points to the retrained Mobilenet model file we generated earlier. Then, we specify the image we want to classify using the -image flag, ensuring we pass in the image located at tmp lab1.jpg. Now, it's important to define the -input layer and -output layer flags, which tell the model where to look for input and where to output the classification results. We also include flags for image size specifications, like -input height and -input width, both set to 224 pixels, matching the input shape our model expects. Additionally, by setting -input mean and -input stand, we adjust the image normalization to align with the preprocessing applied during training. When we execute this command, it will return classification probabilities for the specified classes, allowing us to assess how effectively our model is doing. For instance, the output could indicate a high probability for the correctly identified class, which is definitely what we want to see. Now, let's implement the following command to create a quantized version of our mobile model. This command launches the retraining process, specifying that we want to generate a quantized model. You'll see this indicated by adding _quantized to the architecture parameter. What we're doing here is optimizing the model for mobile deployment, which is super important for devices with limited computational resources. Now, the -output graph parameter tells us where to save the retrained model. In this case, it'll save as dog retrained Mobilenet 10224 quantized. Similarly, the -output labels parameter specifies the file path for saving the labels associated with our retrained model. This is crucial for understanding the outputs of the model, right? We also need to define the image directory and bottleneck directory where our training images will be stored and where the bottleneck features will be saved, respectively. Together, these parameters ensure that the retraining process aligns with the data we have. This quantization makes the model smaller and faster, which not only enhances performance, but also maintains a decent level of accuracy, making it really well suited for mobile applications. In conclusion, choosing between Inception v3 and Mobilenet ultimately revolves around your project needs. If your primary focus is accuracy and you have the resources to handle those high computational models, then Inception v3 serves you well. However, if you're looking for a responsive and efficient model that works well within the constraints of mobile hardware, then Mobilenet is definitely your best bet. So far, we've covered the basics of performance between Inception v3 and Mobilenet, illustrating these points through retraining processes, benchmark testing, and the impact of quantization. Moving forward, we will delve deeper into real-world applications, discuss additional optimizations, and, address some common pitfalls that developers face when deploying these models on mobile devices. Thank you for joining me, and let's keep exploring the fascinating world of mobile AI. So, when should we use an Inception v3 or Mobilenet retrained model on mobile devices? This question is crucial for developers as they figure out which model to implement in their applications. The decision between these two models really depends on your project's specific needs, especially when it comes to accuracy and speed. In this video, we're going to dive deeper into how to evaluate the performance of both models and see how to decide which one fits various use cases. So far, we've compared the performance of Inception v3 and Mobilenet, shedding light on the trade-offs between accuracy and resource consumption. We've also looked into the retraining process for Mobilenet and discussed how quantization impacts the efficiency of models for mobile applications. Through practical examples in TensorFlow, we've set up and tested these models, highlighting the importance of selecting the right model based on your project requirements. Moving forward, we'll focus on real-world applications and different optimizations to deploy these models effectively. Let's kick off with a fundamental understanding of the Inception v3 and Mobilenet models. Inception v3 is a well-known architecture specifically designed for larger-scale datasets. It combines various convolutional filters in parallel at each layer, which allows it to learn richer feature representations. Now, because of its depth and architectural complexity, Inception v3 usually yields higher accuracy, especially in intricate image classification tasks. However, that complexity also means it has a hefty resource requirement, consuming a substantial amount of memory and processing power. This makes it less suitable for mobile environments, particularly older or less capable devices. On the flip side, we have Mobilenet, which is optimized for mobile devices right out of the box. It's specifically engineered for edge computing environments, achieving comparable accuracy in image classification, but with significantly lower computational resource consumption. This is made possible through depth-wise separable convolutions, which essentially break down convolutions into a two-step process. This results in fewer parameters and less computational overhead. For instance, while Inception v3 has over 25 million parameters, Mobilenet can achieve similar classification accuracy with as few as 4 million parameters. You can see why it's a fantastic choice for mobile applications. Now, let's implement the command to retrain our Mobilenet model using TensorFlow. In this command, we'll specify the output paths for the retrained model and its corresponding labels, which makes it easy to retrieve and use later on. The -output graph parameter is key here, as it designates where the trained model will be saved, while the -output labels identifies the file that contains the class labels corresponding to the model's output. Next, we'll indicate the directory containing our training images using the -imagedir flag. It's really important that this path is accurate, as it points TensorFlow to the dataset you'll be using for retraining. The -architecture parameter is quite crucial too. Here, it specifies that you're utilizing the Mobilenet variant with a size of 1.0 and image dimensions of 224 by 224 pixels, which is optimal for many mobile applications. Additionally, the -bottleneckdir option holds significance because it designates where to store bottleneck features. Now, these features are essentially condensed representations of input images that speed up training by allowing us to skip over redundant calculations. Overall, this command really streamlines the retraining process, letting you customize and optimize your Mobilenet model swiftly. Now, let's see how we can implement the benchmarking of our quantized Mobilenet model to evaluate its performance. To do this, we'll use the Benchmark Model tool provided by TensorFlow, which lets us assess how efficiently our model runs. The command starts with the path to the benchmark tool, followed by the .graph flag, where we specify the path to our quantized model file. It's crucial that this model has undergone quantization, which optimizes it for mobile inference. Next, we need to define the model's input configurations. The .input layer parameter indicates the name of the input layer, while .input layer shape specifies the expected shape of the input data. It's a 1 by 299 by 299 by 3 shape, corresponding to a single image resized to 299 by 299 pixels, with 3 color channels. Using .input layer type, we declare the data type of the input layer. For Mobilenet, this is typically float. Now, we also specify the .output layer parameter to indicate where the model's final classified results are collected. The flags .showRunOrder, .showTime, and .showMemory set to false allow us to focus on the summary of performance metrics provided by the benchmark, which is essential for assessing how our model meets speed and efficiency requirements in a mobile context. Finally, setting .showSummary equals true ensures we receive a detailed summary of the testing results, which will help us make informed decisions about deploying our model. Now, let's implement the code for running Inference with the Mobilenet model in TensorFlow Lite. First, we create an instance of the interpreter, which serves as the interface for running the model. By calling the loadModelFile method, we load the trained Mobilenet model that we converted into TF-Lite format. This step is really crucial, as the model needs to be in a compatible format to optimize performance on mobile devices. Once the model is loaded, we also need to initialize a two-dimensional array called result, which will hold the inference results. Here, num classes represents the expected number of output classes your model can predict. It's important to make sure this variable is set appropriately because it defines the size of the results array. Now, moving on, we execute the run method. We'll pass in the pre-processed input data and the result array. So, this method executes the forward pass of the model using the input data and fills the result array with the predicted class scores. It's crucial to remember that for Mobilenet, the input data must be properly pre-processed to match the model's requirements, including having the correct shape and normalization. Proper pre-processing is key because it ensures that the model provides accurate predictions based on the input. Now, let's implement quantization when retraining your Mobilenet model to optimize its performance for mobile devices. By adding a _quantized suffix to the architecture parameter, you're essentially instructing the retraining script to apply quantization techniques. What does this do? Well, it effectively reduces the model size and enhances inference speed. This step is crucial, especially when you're targeting devices with limited storage capacity, as it compresses the model from approximately 17 megabytes to just around 5.1 megabytes. So, this reduction not only makes the model more accessible for deployment across various mobile devices, but it also improves the user experience by enabling faster inference times. And here's the beauty of it. By minimizing accuracy loss while achieving these efficiencies, quantization really becomes an essential strategy in deploying lightweight and responsive model applications. Therefore, incorporating this suffix when specifying the architecture ensures you're leveraging the full benefits of quantization, allowing your Mobilenet to perform effectively in edge computing environments where resources may be constrained. Lastly, let's take a moment to discuss real-world applications. Both models, Inception v3 and Mobilenet, can be applied to various use cases, from image classification in mobile applications to real-time object detection. Developers often gravitate towards Mobilenet for mobile-focused applications, especially in areas like augmented reality, or AR, and instant image recognition features in consumer apps. Meanwhile, Inception v3 shines in back-end processes where accuracy is paramount, such as photo tagging and sorting within online platforms. Ultimately, your decision should take into account the nature of your application. If you need quicker responses with a slight trade-off in accuracy for mobile devices, go for Mobilenet. However, if the highest accuracy is non-negotiable and resources aren't a concern, then Inception v3 would be the way to go. Now, in conclusion, the journey doesn't end here. As you continue to learn and explore these models, remember to assess their performance in your specific context. Analyze the trade-offs, experiment with optimizations, and most importantly, keep the user experience front and center in your development. Thank you for tuning in, and I hope you now have a greater understanding of how to evaluate and implement the Inception v3 and Mobilenet models. Be sure to subscribe for more deep dives into TensorFlow and machine learning. Today, we are going to embark on an exciting journey to benchmark the performance of Mobilenet models against the well-known Inception models. You know, understanding these benchmarks is really, critical for selecting the best model for your mobile applications. We've already learned about the architectural distinctions between Inception v3 and Mobilenet, emphasizing factors like portability and efficiency. Now, we're going to cover how to accurately benchmark these models using TensorFlow. Let's sprinkle in some practical code examples to illustrate these benchmarking techniques. So, if you're curious to see how it all works, stay tuned. This is going to be a valuable experience for anyone looking to optimize their mobile applications. Let's explore the process of creating the benchmark model tool using TensorFlow's source code. This initial step is vital before we can conduct any performance evaluations of the different models we plan to assess. The command we will use is tailored to compile all essential files with optimized settings, resulting in a benchmark model executable that we can utilize in the following stages. Next, we will construct a command to run the benchmark model against a specific Inception v3 model. This command plays a key role as it outlines various parameters that enable us to analyze the model's effectiveness. For example, we will identify the graph file, which refers to our pre-trained model, and designate the input layer as mul, along with its related shape. The characteristics of the input layer are critical, as they allow the benchmark tool to comprehend the data format and the dimensions of the images it needs to handle. Once we execute this command, the tool will provide us with valuable performance metrics, such as the number of floating point operations per second, flops. This data is particularly important for assessing the model's computational requirements. In this particular scenario, if we observe a result of approximately 11 billion flops, it highlights the resource-intensive nature of this Inception model, helping us evaluate its performance on a range of devices, particularly older ones like the iPhone 6. Now, let's dive into how we can benchmark a Mobilenet model using the benchmark model utility. To start executing this, we'll need to swap out the graph file parameter with our Mobilenet model file, which, by the way, is crafted specifically for images that are sized at 224 by 224 pixels. In the command, we will specify the input layer as mul and denote the input layer shape as 1, 224, 224, 3. This means we're processing a single image that has 3 color channels. Yeah, that's RGB. The command also notes that the data type for this input layer is float, which is really the standard for images in deep learning tasks. After that, we define the output layer as final_result, and we configure a few flags to make the output more streamlined. For instance, we set -show run order, -show time, and -show memory all to false to cut down on verbosity, while we turn -show summary to true so we get a nice, neat overview of the benchmarking results. Running this command will give us some essential performance metrics, including the estimated flops, which really showcases the computational efficiency of the Mobilenet model, especially when we stack it up against more demanding architectures like Inception v3. This comparison, you see, is super important when picking models that are optimized for mobile applications, where speed and resource efficiency are, by the way, absolutely critical. Now, let's implement the following command to retrain a Mobilenet model tailored for our specific image classification tasks. This command makes use of the retrain.py script, which you'll find in the TensorFlow examples directory. First off, we need to specify a destination for our output graph file. This is where our retrained model will be saved, and it will allow us to use the model for inference later on. For this exercise, we'll designate it as /tf files /dog retrained mobilenet10 pb. Next, it's essential to save the output labels that correspond to our classifications in a text file. We'll set that to /tf files /dog retrained labels mobilenet.txt. This file is key for keeping track of the different classes the model will predict, making it easier for us to analyze the model's outputs. Now we'll also provide the -imagedir parameter, which points directly to the directory where our training images are stored. This step is vital since it tells the script exactly where to find the data needed for the retraining process. To boost our model's performance even further, we will set the -bottleneck dir, which stores those handy pre-computed bottleneck features. Finally, we need to specify the architecture of the Mobilenet model that we're using. In this case, it's Mobilenet 1.0 224, which strikes a nice balance between portability and accuracy, ensuring that our model remains efficient for mobile deployments. Now let's explore how to test the newly trained Mobilenet model using a specific image. We'll implement a command that runs inference on the input image located at tmp/lab1.jpg. This command utilizes the label image tool, which processes the model graph that we retrained and saved in tf files dog retrained mobilenet10 224. You see, the parameters like -input layer and -output layer specify the specific layers of the model we want to use for input and output. This ensures that the data is correctly routed for classification. Now we also need to specify the labels used for the model in the -labels parameter, pointing to the file that contains the class names tied to our retrained Mobilenet model. Additionally, image dimensions are critical for successful inference, so we set dash input height and dash input width to 224, which matches the specifications of the Mobilenet model. Now, to get the best classification results, we further normalize the input data using dash input mean and dash input stand parameters, which standardizes the input and enhances classification performance. As a result, the tool will output the most likely classifications along with their corresponding confidence scores, which will indicate the model's certainty regarding its predictions. Next, we're going to write a command to retrain our Mobilenet model with quantization, which will really enhance its performance for mobile applications. So, this command, it utilizes TensorFlow's retrain script and includes several important parameters. So let's break those down together. The dash output graph argument specifies the path where our quantized model will be saved, which in this case will be dog retrained Mobilenet 10 224 quantized. This model is optimized for inference, reducing the size significantly, making it ideal for mobile devices. Now, moving on to the dash output labels parameter, this is where we indicate where to save the label file, which contains the classifications associated with our model. This part is crucial for correctly interpreting the model's predictions. Then we have the dash imagedir parameter, which tells the model where to find the training images, allowing it to learn effectively from this dataset. Let's not forget the dash bottleneckdir, which is where we store the bottleneck features. These are pre-computed representations of the images that help speed up the retraining process. Finally, the most crucial addition here is the dash architecture parameter, and we set that to Mobilenet 1.0 224 quantized. This indicates that we're using a specialized quantized version of the Mobilenet architecture that keeps that efficiency while delivering faster inference speeds and lower memory usage. This command is an exciting step towards optimizing your model for deployment. Lastly, as we look to maximize performance while keeping accuracy in check, remember that choosing the right model is really about your specific application needs. If you're aiming for ultra-fast inference and you're working with a resource-limited device, quantized Mobilenet will actually outperform the more complex models. But, on the flip side, if you're in a scenario where accuracy is crucial, then Inception v3 is definitely a strong contender. In conclusion, benchmarking, retraining, and optimizing models are essential skills for any machine learning practitioner, especially when you're developing for mobile platforms. By effectively leveraging TensorFlow's tools, you can make sure your applications strike that perfect balance between being performant and effective. Thank you for joining me in this exploration of benchmarking Mobilenet against Inception models. I truly hope these insights help you as you work on your projects. Now, have fun experimenting.
One tool to give you an accurate benchmark of a model is Benchmark Model. In this video, we will dive deep into the benchmarking performance of Mobilenet and Inception models, exploring what sets them apart and why it matters in the world of mobile applications. We'll also cover essential concepts, utilize TensorFlow's benchmark model tool, and provide practical code examples specifically for Android and iOS development. Now that we have TensorFlow set up in our project, let's dive into the code responsible for loading our models for benchmarking. For Android, we begin by importing the necessary TensorFlow Lite libraries to facilitate model interpretation. We create a class called ModelLoad with a method, loadModel, that initializes the interpreter. This method takes a model path as an input, allowing us to specify where our TensorFlow model file is located. By establishing a file input stream linked to this path, the interpreter can load the model, enabling us to run inference during benchmarking. On the iOS side, we implement a similar structure in a class named ModelLoader. Here, we declare an interpreter variable and provide a loadModel method. This method also accepts a model path and initializes the interpreter, allowing it to interpret the model for inference. By having these methods, we ensure that both our Android and iOS applications can seamlessly access and utilize the models we'll benchmark, setting the stage for performance evaluation. Next, let's see how we can implement the benchmarking functions to analyze the latency and accuracy of each model in action. Now let's see how we can implement the model loading functionality for both Android and iOS platforms. In the Android code, we start by importing the necessary TensorFlow Lite interpreter class, along with libraries for file handling. We then define a class named ModelLoad, which contains a private instance of the interpreter. The core functionality is encapsulated within the loadModel method, where we create an instance of the interpreter using a file input stream that reads the model from the specified model path. This setup allows the app to load the model efficiently, preparing it for inference. Similarly, in the iOS code, we import the TensorFlow Lite framework and define a class called ModelLoader. Here, we declare an optional interpreter variable. The loadModel method in this class attempts to initialize the interpreter by providing the model path. If successful, this method allows us to prepare the model for execution. Together, these implementations ensure that we have the necessary infrastructure to load the Mobilenet and Inception models in our benchmarking process, enabling TensorFlow to interpret them for further evaluation and performance analysis. Now let's implement the benchmarking functions for both Android and iOS. For the Android version, we define a method called benchmarkModel. This method begins by capturing the current time in nanoseconds before executing the model's inference using tflight run, passing in the input data and receiving the output. Once the inference completes, we calculate the duration by subtracting the starting time from the current time again. Finally, this duration is converted from nanoseconds to milliseconds and printed to the console, providing a clear measure of how long it took for the model to process the input. Next, we will write the iOS version of the benchmarking function. In this version, we create a function called benchmarkModel that accepts the input data as a parameter. Similar to the Android implementation, we record the start time using dispatch timenow. After copying the input data to the model's input and invoking the interpreter, we again record the end time. We then calculate the duration in a similar fashion, converting it to milliseconds before returning this value. Together, these functions enable us to effectively measure and analyze the latency of both models during inference, which is a crucial aspect of performance benchmarking. Now let's implement a function to evaluate the accuracy of our model's predictions against the actual outputs. In the Android implementation, we define a method that takes two arrays, one for the predicted values and another for the actual expected outputs. The function iterates through the predictions, comparing each value with the corresponding actual output. For each match, it increments a counter that tracks the number of correct predictions. Finally, we calculate the accuracy as the ratio of correct predictions to the total number of predictions, multiplied by 100 to express this as a percentage. This gives us a straightforward metric representing how well the model is doing. Next, we'll see how we can achieve the same functionality in iOS. In this version, we use a function that also accepts two arrays, one for the predictions and one for the actual outputs. As in the Android implementation, we iterate through the predictions, counting how many match the actual values. After processing all predictions, we return the calculated accuracy percentage. This method not only provides insight into the model's performance, but also helps developers understand its effectiveness in practical applications, ensuring that precision is maintained when deploying models in real-world scenarios. Next, we will look at how to log resource usage during our benchmarks. For Android development, we use the debug class from the Android API to monitor memory usage. We define a method that retrieves the native heap size currently allocated, providing an insight into how much memory is being utilized by our application. This information is crucial, especially in mobile environments where memory efficiency can significantly impact performance and user experience. Now let's see how we can implement a similar functionality for iOS applications. In the Swift code, we measure the application's memory footprint, converting it to kilobytes for easier readability. This approach allows developers to keep track of the memory consumption as the model processes data, ensuring that they can identify any potential bottlenecks or areas for optimization. By consistently logging and evaluating resource usage like memory, CPU load, and battery consumption, we can enhance our application's performance and create a better experience for users. Keeping these metrics in mind as we benchmark will ultimately help us achieve a more efficient mobile application. Now let's take a look at how we can effectively display the benchmarking results for both the Mobilenet and Inception models. In our code, we have defined two functions, one for Android and one for iOS, both aimed at presenting the performance metrics collected during the benchmarking process. For the Android implementation, we gather 4 key metrics: the inference time and accuracy for both models. The function initializes with the appropriate parameters and utilizes system.out.println to clearly output the results. This approach not only provides immediate feedback but also keeps the information structured, making it easier for developers to understand and compare the performance of both models. Similarly, in the iOS version, we use print statements to showcase the results. The syntax is adjusted to fit Swift's conventions, allowing us to format the output efficiently. By encapsulating this functionality into a dedicated method, we promote code reusability and maintainability, encouraging developers to quickly analyze results without redundant code. These functions serve as a central point where the performance comparisons can be easily referenced and evaluated, supporting informed decision-making in model selection based on the specific requirements of mobile applications. As we wrap up our exploration of benchmarking the performance of Mobilenet and Inception models, remember that accurate evaluation is invaluable. The process of comparing these models using the benchmark model tool in TensorFlow equips you with insights necessary to optimize your application. Understanding the trade-offs between accuracy and performance, as well as resource utilization, can empower you to choose the right model tailored to your mobile application needs. In the coming sessions, we will look at deploying these models effectively on Android and iOS, ensuring that all the benchmarks conducted translate into practical, optimized mobile solutions. Thank you for joining, and I look forward to seeing you in the next. Let's dive into the intriguing world of Mobilenet and Inception v3 models, specifically focusing on what it means to select and benchmark these models for mobile device use. We will explore the key considerations for using these models, from accuracy to performance metrics, while also providing some code snippets so you can see practical applications. So far, we learned about the benchmarking of Mobilenet and Inception models using TensorFlow's benchmark model tool, focusing on their performance metrics like latency, throughput, and accuracy for mobile applications. We covered how to load these models in both Android and iOS environments and implemented benchmarking functions to assess their inference times and accuracy against a dataset. Additionally, we discussed the importance of resource usage metrics such as memory and CPU load, which are crucial for optimizing mobile app performance. Now, we will explore effective deployment strategies for these models on mobile platforms. Now let's see how we can set up our TensorFlow environment to benchmark both the Inception v3 and Mobilenet models. First, we need to install TensorFlow by running a simple pip command, which ensures we have the necessary libraries and tools at our disposal for benchmarking. Once TensorFlow is installed, we need to build the benchmark model tool using Bazel. This process involves compiling the necessary components optimized for performance, which prepares us to run our benchmarking tests. Next, we will conduct a benchmark test specifically for the Inception v3 model. This test will involve executing a command that specifies the path to the graph file of the retrained Inception model, alongside the input shapes and output layer details. This command not only analyzes the performance of the model, but also provides us with a summary of performance metrics, such as the number of floating point operations, flops, needed for inference. Then we will shift our focus to the Mobilenet model, utilizing a similar command structure but adjusting the graph file path to point to our Mobilenet model. This benchmarking test will likely yield a significantly lower flop count, showcasing Mobilenet's efficiency for mobile environments. By comparing these results, we can better understand each model's performance and make informed decisions based on our application's needs. Now let's see how we can initiate the retraining of a Mobilenet model tailored for our image classification tasks. The command we are using specifies several crucial parameters that guide the training process and the output of our model. We start by defining the output graph file, which is where our retrained model will be saved. This file contains the architecture and weights of the model after it has undergone training with our specific dataset, allowing us to use it later for inference. Next, we set the output labels file, which will list the classes recognized by the model based on our training images. This is essential for interpreting the predictions our model makes. The image directory parameter points to the location of our training images, and the bottleneck directory holds processed images that speed up the training process. Most importantly, we specify the architecture of Mobilenet to be used, 1.0 with an input size of 224, which balances accuracy and performance. If a quantized version is required for efficiency, we can replace the architecture parameter accordingly, resulting in a smaller model size vital for mobile deployment. This entire command streamlines the process of preparing our Mobilenet model, making it ready for effective deployment. Now let's implement the following command to evaluate our retrained Mobilenet model on a specific image. This command is essential for testing the model's performance and obtaining classification results based on the image provided. We specify the path to the graph file, which contains the model architecture we have fine-tuned, ensuring it aligns with the Mobilenet settings. The image file is indicated next, pointing to where our test image is located. This is the image the model will analyze to generate predictions. The code also defines the input and output layers used within the model. In our case, the input layer prepares the data for processing, while the output layer returns the final classification results. Furthermore, setting the input height and width to 224 ensures that our image is correctly preprocessed for Mobilenet's expected input dimensions. We also include parameters like input mean and standard deviation, which normalize the data to ensure the model can accurately interpret the input image. After executing this command, we can expect a confidence score for each classification, giving valuable insights into the model's performance and aiding in further optimization or training iterations. Now let's implement the following code to load our TensorFlow Lite model in an Android application. This snippet demonstrates how to initialize the TensorFlow Lite interpreter, which is critical for running inference on our model. In this code, we start by using a try-with-resources statement to create an instance of the interpreter class. This ensures that the interpreter is properly closed and released from memory once we're done using it. The method loadModelFile is called to load the TensorFlow Lite model from storage, which you must ensure is accessible in your application. Next, we define an input array with the dimensions required for our model. In this case, it accepts an image size of 224 by 224 pixels with 3 color channels, RGB. This array will contain the input data that we want to classify. Similarly, we create an output array that will store the model's predictions, prepared for as many classes as defined by num classes. Calling tflight run input output executes the model with the provided input data, populating the output array with the results from the inference. This code snippet is essential for getting predictions from your TensorFlow Lite model efficiently, enabling real-time classification within your mobile application. All in all, the decision between Inception v3 and Mobilenet boils down to your specific use case and optimization needs. If accuracy is paramount, Inception is a great choice, but for mobile efficiency, Mobilenet shines. With the benchmarks and testing methods we've discussed, you now have the tools to make the best choice for your model deployment in mobile applications. Whether you stick with a Mobilenet or delve into Inception v3, understanding your resource constraints and balancing them with your application's needs will lead to a successful implementation. Let's dive into the exciting world of benchmarking Mobilenet performance for inference speed, a crucial aspect in the applications of machine learning models, especially in mobile contexts. As we explore this topic, we'll uncover how to assess and improve Mobilenet's efficiency through concrete metrics like flops, floating point operations per second, and inference speed. So far, we learned about selecting between Inception v3 and Mobilenet models for mobile applications, considering factors like accuracy, performance, and resource constraints. We benchmarked both models using TensorFlow, highlighting their differences in flops and execution time. Additionally, we explored how to retrain and test Mobilenet models for specific applications while discussing the integration process into mobile apps for both Android and iOS. The key takeaway is to choose the model that best fits your application's requirements and performance needs. Now, we will focus on benchmarking Mobilenet's performance for inference speed, providing you with methods and code examples to achieve this. Now let's implement the following code to load the retrained Mobilenet model and prepare a sample input tensor. First, we import TensorFlow, which provides us with the necessary tools to work with our model. By using the tf saved model load method, we can quickly load our Mobilenet model from the specified file path. This step is crucial as it allows us to utilize the pre-trained weights and architecture of Mobilenet for inference. Next, we prepare an example input tensor to simulate the real image input that we would typically use in our application. The dimensions of this tensor are set to 1, 224, 224, 3, where 1 indicates the batch size representing a single image, and 224x 224 represents the height and width of the image in pixels. The 3 denotes the RGB color channels, matching the input requirements of our Mobilenet model. By using TF random uniform, we generate a random input tensor with values that mimic real image data. This step is essential as it prepares the model to accept inputs formatted correctly for inference, setting the stage for further benchmarking of the model's performance. Next, we will write a code snippet to benchmark the inference speed of our Mobilenet model. First, we utilize the Python time module to measure how long it takes to generate predictions based on our input tensor. The code begins by capturing the current time before we run the inference, which involves passing the input tensor to the Mobilenet model. After obtaining the output, we simply calculate the elapsed time by subtracting the start time from the current time after inference completion. Finally, we print the inference time, formatted to 5 decimal places, which gives us a precise measurement of how long the prediction took. This metric is crucial as it helps us assess the performance of the model and determine areas for improvement, especially for applications where responsiveness is key, such as mobile devices. By analyzing this timing information, developers can make informed decisions to optimize their applications based on the model's performance. Now let's take a look at how to include the TensorFlow Lite library in your Android application. To begin, you need to add the necessary TensorFlow dependencies in your build Gradle file. By including implementation org TensorFlow Lite 240 and implementation org TensorFlow Lite GPU 240, you ensure that your project has the capabilities to leverage TensorFlow Lite's optimized features, including GPU support for enhanced performance during inference. Next, we'll implement a Java class called TensorFlow Lite Model, which will handle loading the TensorFlow Lite model and executing inference. The constructor initializes an instance of the interpreter, which serves as the main interface for running your model. It takes the path of the model as a parameter and invokes load model file to read the model file from the assets folder, ensuring proper access while encapsulating the load logic within the class. Finally, we will implement the runInference method, which accepts a two-dimensional array representing input data, such as an image. This method creates an output array for the prediction probabilities and utilizes the interpreter's run method to process the input. This structured approach keeps your code organized and facilitates efficient inference, thus improving the application's responsiveness and overall user experience. Now let's implement the code that benchmarks the inference speed of our Mobilenet model on a mobile device. We begin by initializing a variable total time to accumulate the total execution time across multiple inference runs, setting iterations to 10 for consistent testing. Within a loop that runs for the specified number of iterations, we use system nanotime to capture the start time just before invoking the inference method on our model with a sample input. After the inference completes, we calculate the elapsed time by subtracting the start time from the current time, adding this duration to our total time variable. This process repeats, allowing us to gather several timing measurements. After completing all iterations, we compute the average inference time by dividing total time by the number of iterations and converting this result to milliseconds for easier interpretation. Finally, we output the average inference time to the console. This average provides valuable insight into how our model performs under repeated conditions, enabling us to better anticipate how it will behave on different devices. By analyzing these results, we can ensure that the model meets user experience expectations and maintain all necessary performance standards. In conclusion, benchmarking Mobilenet performance for inference speed takes considerable understanding of both the underlying model architecture and how best to implement it on mobile platforms. Through the code examples provided, we successfully demonstrated how to load and convert Mobilenet models and benchmark inference speed both in TensorFlow and on Android. As you proceed with your projects, keep in mind that the ultimate goal is optimizing for responsive and efficient user experiences while leveraging powerful machine learning capabilities. As we continue on this journey, remember that practice is key. Experiment with different datasets and explore the rich features TensorFlow and TensorFlow Lite can offer. By doing so, you'll not only optimize Mobilenet performance but also elevate your skills and understanding of deploying machine learning models in real-world applications. In June 2017, Google introduced Mobilenets v1, a collection of 16 mobile-first deep learning models designed for TensorFlow. These models are tailored specifically for mobile devices, boasting compact sizes ranging from just a few megabytes while still achieving commendable accuracy. Today, we're diving into an exciting topic: retraining Mobilenet models, breaking down the techniques that make this possible, and equipping you with the skills to enhance your machine learning projects on mobile. So far, we covered the benchmarking of Mobilenet's performance for inference speed, highlighting its importance in mobile applications where quick responses are crucial. We discussed how to measure this speed using TensorFlow and the advantages of TensorFlow Lite for increased efficiency. Additionally, we explored how to integrate TensorFlow Lite models into Android applications and underscored the necessity of conducting benchmarks on real devices to grasp performance thoroughly. Our main focus has been optimizing user experience with swift model inference times as we deploy machine learning solutions. Now we will cover the retraining techniques for Mobilenet models, their architecture, and how you can practically implement them using TensorFlow. Now let's implement the Mobilenet model with TensorFlow by initializing it with pre-trained weights. We start by importing TensorFlow in the Mobilenet class, and then we load the model using the weights from ImageNet while excluding the top classification layer with include top equals false. This allows us to customize the model for our specific task. Next, we add layers to adapt the model's output for our dataset. We perform global average pooling to condense the spatial dimensions, followed by a dense layer with 1024 units and Ray-LU activation to introduce nonlinearity. Finally, we create a softmax output layer with 10 classes to suit our classification needs, wrapping it all together into a new model. Now let's see how we can freeze the base layer's parameters to prevent them from being updated during retraining. We iterate through the layers in the Mobilenet model and set their trainable property to false, ensuring that only our added layers are trained. This method speeds up the retraining process and mitigates overfitting, especially useful when we have a limited amount of data. Once we've done this, we compile the model with the Atom Optimizer and categorical cross-entropy loss function, preparing it for effective training on our specific task. Now let's implement the image data generators necessary for loading and augmenting our training and validation datasets. We begin by creating an instance of the image data generator, where we apply preprocessing techniques to rescale the pixel values of the images to a range between 0 and 1. This normalization helps our model to converge faster during training. Additionally, we enhance our dataset's variability through augmentations, including random rotations, shifts, shears, zooms, and horizontal flips, which simulate different conditions the model might encounter in real-world scenarios. Next, we will generate batches of image data using the flow-from-directory method. This method reads images from specified directories, allowing us to organize our training and validation images accordingly. We also define the target size for the images to be 224 by 224 pixels, which aligns with the input size expected by Mobilenet. By specifying a batch size, we can efficiently manage memory and processing, ensuring smooth data handling as our model trains. This structured approach to data loading and augmentation sets the foundation for the next steps in fitting our model effectively. Now let's evaluate the performance of our retrained Mobilenet model using metrics that will help us understand how well it generalizes to unseen data. First, we call the evaluate method on our final model, passing in the validation data generator. This will compute the loss and accuracy metrics, providing us with insights into how our model performs on the validation set. After running this evaluation, we can print the validation accuracy, formatted to display it as a percentage. This step is crucial as it gives us feedback on whether our retraining has successfully improved the model's performance. Next, we will save the trained model using the save method. This is important because storing the model allows us to reuse it later without needing to retrain, making it easier to deploy in applications like mobile apps. Once we have assessed the performance and saved the model in Keras format, we can proceed to convert the model into a TensorFlow Lite format suitable for mobile deployment. This conversion is facilitated by the TF Lite converter, which simplifies the process of preparing our model for efficient inference on mobile devices. We then save this lightweight model into a TFLite file, ensuring it can be integrated easily into Android and iOS applications, enabling fast predictions in a production environment. Now let's see how we can implement inference using our retrained Mobilenet model in an Android application. The code starts by initializing an instance of the TensorFlow Lite interpreter, which is responsible for executing the model inference. We load the TFLite model file that we previously converted and saved. This is crucial because the interpreter needs to reference the model's structure and parameters to function correctly. Next, we prepare the input and output arrays. The input array is defined to accommodate a single image in the shape required by the model, specifically a 224x224 image with 3 color channels, RGB. The output array is set up to hold the results from the inference, which in this case assumes 10 classes for classification. Once our input data is prepared, we call the run method of the interpreter. This method takes the input data and processes it through the Mobilenet model, ultimately populating the output array with predictions. The resulting output array will contain the model's confidence scores for each of the 10 classes, enabling us to understand which category the input image most likely belongs to. Retraining Mobilenet models presents an efficient solution for deploying custom machine learning workflows on mobile devices. Once again, the strengths of Mobilenet come from its small footprint and excellent adaptability to various tasks through transfer learning. Remember, each step from loading data, retraining, to deployment requires careful consideration to maintain performance. We've covered a lot of ground, and I hope this lesson equips you with the foundational knowledge to harness Mobilenet for your applications. Remember, it's all about experimentation and practice to master these concepts fully. So dive in, get your hands dirty, and start retraining those Mobilenet. When it comes to deploying deep learning models on mobile devices, selecting the right architecture can significantly impact both performance and accuracy. Today, we'll dive into comparing two noteworthy models, Inception v3 and Mobilenet, helping you understand when to use each depending on your specific needs and constraints. So far, we covered Google's Mobilenets v1, emphasizing their efficiency and speed tailored for mobile applications. We discussed their architecture and how to set them up in TensorFlow for effective retraining. Now, we will analyze the unique attributes of Inception v3 and Mobilenet, comparing their capabilities and use cases in mobile environments. Now let's see how we can benchmark Inception v3 using TensorFlow's provided tools. The command initiates the benchmarking process with benchmark model, where we specify the path to the graph file that contains our retrained and quantized model, which in our case is located at /tf-files/quantized-strip-dogs-retrained, pb. In this command, we define several parameters to correctly configure our input. The input layer parameter specifies the layer we want to use as input, labeled as mul. We also need to inform TensorFlow about the shape and type of our input data through input layer shape equals 1/299/299/3 and input layer type equals float. This means that we are working with a single image of size 299x299 pixels, and it has 3 color channels, RGB. Moving forward, we specify the output layer using output layer equals final result, which is where the model's predictions will be generated. To keep our results focused and streamline the output, we disable options that display run order, time, and memory usage by setting the respective flags to false, while opting to see a summary of the results with show summary equals true. This benchmarking will provide valuable insights, particularly the estimated floating point operations, flops, which helps assess the computational intensity of the model on mobile devices. Now let's implement the following command to retrain a Mobilenet model tailored to our custom dataset. This command will leverage TensorFlow's image retraining capabilities, aiming to create a new model fitted to recognizably classify images of dogs from our specified image folder. We first direct the system to save the trained model to a specific location using the output graph parameter, ensuring we can easily access the model later for inference. The output labels parameter points to a text file containing our dog class labels, which will be generated after retraining. Next, the image dir parameter indicates where our training images are stored. This is crucial as TensorFlow will pull images from this directory to train the model. The bottleneck dir parameter is set for storing bottleneck files, which speed up the retraining process by reducing the needed computations when feeding images into the neural network. Finally, we specify the architecture with the architecture option. By using Mobilenet 1.0.224, we are selecting the larger version of Mobilenet optimized for images of size 224x224 pixels, allowing us to balance model complexity and accuracy effectively. This comprehensive command enables efficient retraining, adapting Mobilenet to our specific image recognition task. Now let's see how we can run inference with a retrained Mobilenet model to predict object labels efficiently. The command begins by calling the label image executable from the TensorFlow examples directory. It points to our trained model graph file using the graph flag, ensuring that we're leveraging the correct architecture fine-tuned for our specific classification task. Next, we specify the image we want to analyze with the image parameter, which shows the path to the input image. We also need to define the input and output layers of the model using the input layer and output layer flags, ensuring that the model knows where to find the input data and where to send the output predictions. These layers must match the specifications defined during the model training phase. Additionally, we set the input dimensions with input height and input width, both of which are critical since Mobilenet typically expects input images of 224 x 224 pixels. Lastly, we adjust the image's mean and standard deviation values with input mean and input STD, which helps standardize the input data for better prediction accuracy. This setup enables Mobilenet to provide quick and accurate predictions, making it ideal for real-time applications like augmented reality. Another consideration when choosing a model is device capability. While Inception v3 could turn out to be excessive for lower-end devices, Mobilenet can easily run on a wide range of smartphones without running into performance issues. The dramatic difference in battery consumption between the two models can be a deciding factor, especially in a mobile usage context where conserving battery life is essential. In environments where high accuracy can afford to lose a bit of speed, Inception v3 shines, but installing TensorFlow Lite could prove resource-heavy. For developers building applications with real-time image processing loops, Mobilenet would make much more sense as it holds a clear advantage in responsiveness and seamless integration. Lastly, the deployment process for Inception v3 involves a user more formidable than Mobilenet due to its considerable model file size and execution time. Not only does Mobilenet produce lighter models, but it also supports quantization, making the models even smaller without drastically impacting performance. Choosing a model with quantization often allows developers to fit their applications more comfortably within mobile constraints. In summary, both models serve essential roles in mobile development. Inception v3 offers high accuracy for computationally capable devices, while Mobilenets provide something powerful but small enough for efficient running on more resource-constrained mobile platforms. Going forward, it's worth considering your application's specific requirements and the target audience's device capabilities when making a decision. With that, you can effectively choose the model that enhances user experience and meets performance expectations while working within your constraints. The comparison we've explored between Inception v3 and Mobilenet should give you a solid foundation to guide your future project decisions in mobile application development. In this session, we dive into the fascinating world of Mobilenet model benchmarking, particularly focusing on its inference speed. Mobilenet has transformed deep learning applications on mobile devices by significantly reducing the resource footprint while preserving high accuracy. Today, we'll explore how to utilize Mobilenet for efficient inference, review benchmark results, and see practical coding examples that showcase its implementation. So far, we covered the differences between Inception v3 and Mobilenet, emphasizing Mobilenet's efficiency in resource-constrained environments compared to Inception v3's heavier resource demands. With a solid understanding of these two architectures, we're now ready to delve into Mobilenet benchmarking and how we can measure inference speed. Before we jump into the coding examples, let's analyze an interesting result from our previous benchmarks. By replacing the graph file with the retrained Mobilenet model, specifically DOG retrained Mobilenet 10224, PB, we noted that the flop's estimate became about 1.14 billion. That's an astonishing increase in speed, almost 10 times faster than some of the alternatives. Now let's see how we can implement the loading of the Mobilenet model and run inference in our application. First, we create an instance of the TensorFlow Lite interpreter, which is a crucial step as it allows us to utilize the Mobilenet model optimized for mobile devices. It's important that the model file we load is in the correct format, specifically with the tflight extension, because TensorFlow Lite is designed for such usage. Next, we prepare the input image by initializing a multidimensional array that matches the input shape expected by Mobilenet, which is typically 224 x 224 pixels with 3 color channels, RGB. This input array will need to be filled with normalized pixel data from the image you want to classify. After we set up the input data, we define an output buffer that matches the number of classes relevant to your specific classification task. This buffer will later hold the model's predictions. Finally, we execute the inference process using the run method, passing in our prepared input and output buffers, which allows the model to process the input and generate results effectively. Now let's see how we can measure the inference time for our Mobilenet model on a mobile device to evaluate its performance. We achieve this by capturing timestamps before and after the inference process using system nanotime. First, we initialize a variable to store the start time right before we call the run method of the TensorFlow Lite interpreter, which executes the model inference with our input data. After the inference is completed, we again capture the timestamp to mark the end of the operation. The next step involves calculating the difference between the end time and the start time to determine how long the inference took. To convert the result from nanoseconds to a more interpretable unit, we divide the difference by 1,000,000. This gives us the inference time in milliseconds, which is crucial for understanding the model's efficiency. Finally, we print out the inference time so that developers can analyze the performance metrics directly. Keeping an eye on inference times can greatly enhance user experience, especially in applications requiring real-time processing, such as image classification on mobile devices. Now we've seen how to measure the inference speed, let's discuss the implications of these metrics in practical applications. The primary benefit of using Mobilenet is its ability to operate in real time with limited computational resources. For instance, let's say we are developing an augmented reality application that requires instantaneous object recognition. If our inference time falls below 100 milliseconds per frame, users are likely to experience a smooth and responsive interaction. However, exceeding that threshold could lead to noticeable lag, negatively impacting the user experience. To illustrate this, imagine you are working on a mobile application designed to recognize dog breeds. Your model's performance may directly correlate with user satisfaction. In this case, leveraging Mobilenet makes perfect sense due to its structure designed to provide a high-speed inference while maintaining reasonable accuracy levels. Therefore, during our benchmarking, targeting different devices or scenarios could reveal various insights into how well our model meets these application-specific performance requirements. Next, we will implement a process for converting our trained model into a TensorFlow Lite format, which is particularly useful for deployment on mobile devices. We start by importing the TensorFlow library, which gives us access to the essential tools for model manipulation. Now we will create a converter instance from the saved model, specifying its path. This converter is responsible for transforming our model into a lightweight format suitable for mobile environments. Next, we enable optimizations by setting the converter's optimizations attribute to the default optimization setting, which includes quantization. This is a crucial step as quantization reduces the model size and enhances inference speed, which is vital for mobile applications. Once we configure the converter, we call the convert method to perform the conversion process. This will output the TensorFlow Lite model, now compressed and fine-tuned for efficient execution. Finally, we save the resultant model to disk as a tflight file, which can be used in our mobile application. This entire process allows us to leverage the benefits of TensorFlow Lite, ensuring our model is optimized for real-time performance while minimizing resource use. We also need to benchmark the quantized model in the same way we did with the original. This allows us to compare performance metrics directly, leading to informed decisions about which model to deploy in production. Not only does quantization typically lower inference time, but it can also considerably reduce the size of the model, which is a crucial aspect for mobile app developers concerned with application download size. To run performance comparisons, one could use both a floating point and a quantized model with identical datasets for inference and measure the differences in runtime and accuracy metrics effectively. Such benchmarking can take considerable effort but can lead to significant enhancements in application performance and user experience, now and in the long run. In conclusion, we delved deeply into Mobilenet model benchmarking, focusing on inference speed as a primary measure of performance. We explored what FLOPS means, loaded models into our mobile applications, executed inference, and measured performance with practical coding examples. So far, we learned about the importance of inference speed and how to measure it effectively. We've also covered optimizations such as quantization that can help enhance Mobilenet's performance on mobile devices. Moving forward, we will explore advanced techniques for deploying models and engaging users through predictive analytics, making our applications more intelligent and contextual. With our deep understanding of Mobilenet established, it sets the stage for further exploration and allows us to leverage these models in exciting new ways. The world of deep learning on mobile is at our fingertips, and it's time to embrace. In today's lesson, we're diving deep into the intriguing world of deep learning models, specifically focusing on when to choose between Inception v3 and Mobilenet for mobile devices. This decision can significantly affect the performance of your applications, especially regarding speed and accuracy. So let's get right to it. So far, we have learned about the significance of inference speed in evaluating Mobilenet's performance and the role of flops as a measure of computational efficiency. We've discussed how to implement Mobilenet in mobile applications, execute inference, and measure performance with practical coding examples. Additionally, we have explored optimizations like quantization to improve model efficiency and speed, ensuring better user experiences. Moving forward, we will delve into advanced techniques for deploying models and enhancing user engagement through predictive analytics. Now let's see how we can benchmark deep learning models such as Inception v3 or Mobilenet to evaluate their performance. The code provided utilizes TensorFlow's benchmarking tool to assess the inference speed of a model, which is essential for understanding its efficiency on mobile devices. We begin by specifying the path to the pre-trained model graph file that has been quantized and stripped of unnecessary operations, thereby optimizing it for faster inference. Next, we define the input layer, indicating the layer responsible for feeding data into the model. The input layer shape is set to accept images of dimensions 299 x 299 with 3 color channels, suitable for color images. The input type is designated as float to accommodate the data type of our model inputs. The output layer, named final result, is echoed to showcase the final predictions the model produces. Throughout the command, we've also chosen to suppress display options related to run order, time, and memory usage. However, setting the show summary flag to true allows us to view a summary of test results, including the critical flops, floating point operations per second metric, which helps us quantify the model's computational demands during inference. This benchmarking will provide insights into the speed differences between Mobilenet and Inception v3, reinforcing our understanding of how to optimize models for mobile applications. Now let's implement the following command to retrain a Mobilenet model using TensorFlow's Retrain script. In this code, we first specify the output graph parameter, which designates the path where the retrained model will be saved, allowing you to easily access the updated model after training. The output label's argument specifies where the label file will be stored, which is crucial for mapping the model's predictions back to the original classes of your images. Next, we indicate the image dir parameter, pointing to the directory that contains the images you'll use for retraining. This folder should ideally include a variety of images representative of the classes in your dataset. The bottleneck dir argument refers to a directory intended for storing bottleneck features, which helps improve the efficiency of retraining by bypassing unnecessary computations for similar images. Lastly, we set the model architecture using the architecture flag, with Mobilenet 1.0.224, indicating that we are using the full version of Mobilenet with an input size of 224 x 224 pixels. This setup is beneficial for applications aiming to leverage Mobilenet's efficient architecture, ultimately facilitating quick and effective model training tailored for mobile environments. Now let's see how we can test our retrained Mobilenet model using the label image tool, a straightforward method to evaluate its performance on image classification tasks. The command starts with invoking the label image executable, which allows us to process an image through our model. We specify the graph parameter to point to our retrained model file, which contains the learned weights of the Mobilenet. The image parameter indicates the path to the image we want to classify, and it should be a representative example of the type of content the model was trained on. To ensure the model interprets the image correctly, we define the input and output layers, essential for communicating how data flows through the model. Additionally, we set the dimensions of the input image, specifically its height and width, required for the Mobilenet architecture, typically 224 x 224 for this scenario. Lastly, we incorporate normalization parameters, the input mean and input standard deviation, to help preprocess the input image. This adjustment ensures that the model processes the image effectively, setting the stage for test outcomes that include predicted labels along with confidence scores, thereby allowing us to assess the quality of our retrained model. Now let's implement the following command to quantize our trained Mobilenet model. This command uses TensorFlow's graph transformation tool, which optimizes the model specifically for mobile deployment. We begin by specifying the input graph, which is your previously trained Mobilenet model saved as a protobuf file. Next, we define the output graph name where the quantized model will be stored, ensuring that we keep the original model intact for future use. The transformation we apply here is quantize weights, which efficiently reduces the model's weight precision. This process condenses the model size, making it lighter and faster while maintaining an acceptable level of accuracy. By doing so, we can deploy our model on mobile devices without sacrificing performance. This command highlights the importance of model optimization techniques like quantization, which can significantly enhance inference speed and decrease memory usage, thus ensuring a better user experience. Remember, the right optimizations can make a crucial difference in the performance of applications running on resource-constrained environments. In conclusion, the choice between Inception v3 and Mobilenet does not come down to which is better overall, but rather which is better suited for the task at hand. Analyze your application's specific requirements, keep your users in mind, and make an informed choice that balances speed, efficiency, and accuracy. The world of deep learning can be complex, but with these insights and practical coding examples, you're well equipped to navigate it successfully. That's all for today. After this session, you should feel more confident in choosing the right model for your application. Next, we'll explore the advanced techniques for deploying models and enhancing user engagement through predictive analytics, so stay tuned for more insights along the journey of mastering TensorFlow on mobile devices. When it comes to deploying machine learning models on mobile devices, choosing the right model is crucial. Today, we're diving into Mobilenet model performance considerations and discussing when to use it versus models like Inception v3. So far, we learned about the differences between Inception v3 and Mobilenet, specifically how their performance metrics differ based on the application needs. We highlighted Mobilenet's efficiency in mobile environments and discussed techniques for optimizing these models. Now, we will cover how to assess which model to use in mobile applications, specifically focusing on deployment strategies, performance benchmarks, and practical examples. Now let's see how we can execute a benchmark for our Mobilenet model using TensorFlow. The first command builds the benchmark model, optimizing it with the copt flag for better performance. Once built, we can run the benchmark model by specifying various parameters, starting with the path to our Mobilenet graph file. This is crucial as it allows the benchmark tool to load and analyze our specific model. We set the input layer to mul, which indicates the operation within the graph where the input begins. The input layer shape is defined as 12,242,243, which corresponds to the expected dimensions of input images, indicating a single image with a resolution of 224 by 224 pixels and 3 color channels. The command also specifies the output layer as final result, which tells the benchmark where to retrieve the model's output. We can choose to omit additional details like execution order, time, and memory usage by setting their respective flags to false while opting to show just the summary of the performance metrics. By examining the output, such as floating point operations per second, flops, we can gauge the model's efficiency, aiding in decision-making for deployment strategies. Now let's see how we can retrain the Mobilenet model with our specific dataset. The command begins by invoking the retraining script located in the TensorFlow example directory, followed by specifying the output graph file where our retrained model will be saved. This is critical for keeping track of your trained model, as it will be used for inference later. Next, we define the output labels file, which contains the names of the classes the model will learn to classify. We also need to point to the directory that contains our training images. This image directory is essential as it provides the dataset the model will learn from. Additionally, there's a bottleneck directory specified, which holds intermediate feature representations that speed up the retraining process. One of the most important features to customize is the architecture parameter. In our case, we have chosen Mobilenet 1.0.224, indicating we want a version of Mobilenet optimized for higher accuracy, given its larger size. This setup allows us to tailor Mobilenet effectively for our application. Now let's take a look at how we can evaluate our retrained model's performance using another command. This script helps us test the model by classifying a test image, using the previously specified model graph and labels. By examining this output alongside confidence scores, we can gain insights into the model's performance, enabling us to fine-tune our training parameters for better results. Now, let's implement the process to quantize the Mobilenet model, enhancing its performance for mobile applications. The command you will use specifies various parameters vital for creating a quantized version of the model. First, the output graph parameter designates the location where the quantized model will be saved, ensuring that you can easily access this optimized version later. The output labels option similarly points to where the model's label file will be stored, which is crucial for interpreting the model's predictions. The image dir parameter indicates where your training images reside, enabling the retraining process to utilize your specific dataset for better accuracy. Next, the bottleneck dir parameter is used to define a directory for storing bottleneck features, which speeds up the training process by reusing these features across multiple training runs. Finally, the architecture flag is critical as it specifies the quantized model architecture, in this case, Mobilenet 1.0.224 quantized. This indicates that you are opting for a smaller, faster model variant while maintaining an acceptable level of accuracy, making it suitable for deployment in mobile environments. Performance considerations do not stop with model training. We also need to take into account how the models interact with the mobile device hardware. For instance, modern smartphones can often handle tens of billions of flops, which greatly influences your choice of model. Let's say, hypothetically, you're developing an app for an older device like the iPhone 6. Since it can only run about 2 flops per second, an Inception v3-based retrained model might take approximately 5-6 seconds to run Inference. However, using Mobilenet with its modest 1.14 flops, you can achieve Inference in a fraction of that time, delivering a much more satisfactory user experience. As developers, we need to be mindful of these hardware limitations when designing applications. If your model's processing time exceeds acceptable limits, it will likely frustrate users, leading to potential app abandonment. In conclusion, effective model deployment on mobile devices relies on thoughtful selection between Mobilenet and Inception v3 based on speed, accuracy, and device capabilities. So far, we've covered how to benchmark, retrain, and optimize Mobilenet models for mobile deployment. Remember, if you need fast inference for your application, lean towards Mobilenet, whereas for tasks that require utmost accuracy, Inception v3 can be the model of choice, provided the hardware can handle its computational load. Reflect on the application requirements, user expectations, and device capabilities as you deploy your models, ensuring your users enjoy a seamless experience with your app. Our next session will move into user engagement strategies through predictive analytics, tying everything together to create intelligent mobile applications. Thank you for joining today's lesson. Happy coding, and see you in the next video. Let's dive into the world of Mobilenets, a revolutionary step in deploying deep learning models on mobile devices. In June 2017, Google released Mobilenets v1, featuring a total of 16 mobile-first deep learning models for TensorFlow. Are you excited? I know I am. These models were designed to be lightweight and efficient, specifically addressing the challenges of running deep learning tasks on mobile hardware. So far, we learned about the importance of selecting the right model for deploying machine learning on mobile devices, specifically comparing Mobilenet and Inception v3. We discussed Mobilenet's efficiency and the retraining process for customization with specific datasets to enhance accuracy. Additionally, we've explored quantization to optimize model size and inference speed, along with the interaction of models with mobile device hardware. Now we will cover Mobilenets in detail and provide you with practical implementation examples that highlight their capabilities. Let's start by understanding what makes Mobilenets unique. The Mobilenet architecture uses depthwise separable convolutions that dramatically reduce the number of parameters compared to traditional convolutional layers. Essentially, it separates the filtering and feature creation processes, which allows the network to maintain a good level of performance while being efficient enough for mobile devices. This architectural choice makes Mobilenet an ideal candidate for tasks such as image classification, object detection, and segmentation on resources-constrained devices. The overall structure of a Mobilenet consists of a few key components: inputs, depthwise separable convolutions, and fully connected layers. Each of these elements plays a crucial role in model performance and efficiency. Now let's see how we can implement the code to load a Mobilenet model into our Android application using TensorFlow Lite. We begin by importing necessary classes from the TensorFlow Lite library and Java's I/O functionalities to handle our model file. The first critical method defined in the code is loadModelFile, which takes a file object representing the model file as an argument. Inside this method, we create a file input stream to read the file and obtain its size through the file channel. We then map this file to the memory, allowing for efficient reading, which is essential for working with machine learning models on mobile devices. Subsequently, we instantiate an interpreter object, which is responsible for running the inference on our model. This object is initialized with the loaded model file, allowing us to interact with the Mobilenet architecture. Once this is set up, we can run inference on our input data, enabling powerful image recognition capabilities right on the device. This code exemplifies how to set the stage for real-time image processing applications, making the process of leveraging deep learning models straightforward and efficient on mobile platforms. Now let's see how we can customize the Mobilenet architecture to fit our specific dataset, particularly for classifying images of pets. The provided TensorFlow command uses a retrain script, which is designed to fine-tune the Mobilenet model based on a new set of images, enabling it to recognize various pet types more accurately. In this command, we define several essential parameters. First, the output graph flag specifies where to save the newly trained model file, which will hold the updated weights and structure of the customized Mobilenet. The output labels parameter indicates the file where the labels corresponding to the pet classes will be stored, essential for interpreting the model's predictions. Next, the image dir flag points to the directory where the pet images are located, allowing the retrain script to access and use these images for training. The bottleneck dir provides a location to save intermediate representations of the input data, which can help speed up the training process. Lastly, the architecture parameter selects the specific version of the Mobilenet model you're retraining, in this case, the Mobilenet 1.0.224, which is optimized for mobile applications. This entire process enables the model to learn from your unique dataset, enhancing its performance in classifying pet images effectively. Now let's implement the following command to create a quantized version of the Mobilenet model. By appending the quantized suffix to the architecture name in our model command, we instruct TensorFlow to generate a model that is optimized for reduced size and faster inference. Specifically, this is achieved through quantization, a process that simplifies the model by using lower precision calculations, making it more suitable for deployment on devices with limited resources. The resulting quantized model will ultimately lead to a significant reduction in size, from approximately 17 MB for the standard model down to roughly 5.1 MB. This reduction is crucial for mobile applications where storage space is often scarce and performance is paramount. Therefore, by adopting this command, we not only improve the model's efficiency, but also enhance the user experience by ensuring quicker load times and responsiveness during inference. This adjustment is essential for effectively deploying advanced machine learning capabilities while maintaining a lightweight footprint on mobile devices. Now let's take a look at how to implement inference using the TensorFlow Lite model for classifying images of pets. In this example, we define a float array named output, which is initialized to hold the prediction results. This array is structured to accommodate the classifications for different pet types, indicated by num classes, which represents the total number of pet categories the model has been trained on. Next, we utilize the TensorFlow Lite interpreter instance, tflight, to run inference by calling the run method. This method takes two parameters: input data, which contains the preprocessed image data ready for classification, and output, where the inference results will be stored. It is essential to ensure that the input data matches the expected dimensions and scaling for the Mobilenet model, typically normalized to 1, 224, 224, 3, representing a single image with width and height of 224 pixels and 3 color channels, RGB. Once this line is executed, the output array will be populated with the model's predictions, allowing you to determine which pet types are identified with the highest confidence levels. This code snippet efficiently showcases how TensorFlow Lite's capabilities can enable real-time image classification right on mobile devices. Now let's implement the benchmarking process to measure the performance of your Mobilenet model. We'll use TensorFlow's benchmarking tool to evaluate the inference speed and assess the floating point operations per second, flops, which is crucial for understanding how efficiently your model performs on various devices. To start, you'll run a command that specifies your model's graph file and includes essential parameters. The graph flag points to the path of your saved model, allowing the benchmarking tool to access it. The input layer and input layer shape parameters define the input configuration required by the model, ensuring that the data is appropriately shaped for processing. In this case, we're using mul as the input layer name, which is common for models like Mobilenet, with an expected input size of 1x224x224 pixels and 3 color channels. Additionally, the output layer specifies where the model will produce its predictions, and the Show Summary flag enables the display of a comprehensive summary of the performance metrics after the benchmark is completed. By executing this command, you'll receive valuable insights not just on the time taken for inference, but also on the overall efficiency of your model, facilitating comparisons with other architectures and configurations. To wrap this whole session up, Mobilenets are an exceptional tool for deploying deep learning on mobile devices. Their efficiency, coupled with the ease of retraining and quantization, gives developers the power to build sophisticated applications that are not only fast but also relevant to user needs. We've taken a detailed look at how to implement Mobilenets within TensorFlow Lite, customize them for your specific needs, and benchmark performance to ensure optimal use on mobile platforms. Remember, in this rapidly evolving field, staying informed and adaptive is key. The more you experiment with Mobilenets, the more you'll discover their potential in real-world applications. From real-time image recognition to robust classification tasks, the versatility that Mobilenets provide is something every mobile developer should embrace. Thank you for joining me today, and happy. Choosing between Inception v3 and Mobilenet models for mobile device applications can be a critical decision for developers aiming to balance accuracy and speed. Each model has unique advantages that serve different requirements in computer vision tasks. In this session, we will dive into the specifics of when to use Inception v3 versus Mobilenet, considering factors like model size, accuracy, processing speed, and practical scenarios. So far, we have learned about Mobilenets and their significance in deploying deep learning models on mobile devices, starting with the release of Mobilenets v1 by Google. We explored the architecture of Mobilenets, focusing on depthwise separable convolutions, which enhance efficiency for mobile applications. We've also discussed practical implementation steps, including loading models in TensorFlow Lite, customizing models through retraining, and the importance of quantization for optimizing performance. Finally, we touched on benchmarking to measure model efficiency and ensure the best performance on various devices. Now, we will delve into the aspects that differentiate Inception v3 from Mobilenet models, helping developers make an informed choice based on their specific use cases. Understanding the core differences between these two models is crucial to making the right selection. Inception v3 is known for its complex architecture that enables it to achieve high accuracy. It utilizes a variety of convolutional filters at different scales and a mix of pooling operations, which contributes to its ability to capture intricate features within images. This makes it particularly effective for tasks requiring precise image classification, such as identifying objects in complex scenes. With approximately 25 million parameters, Inception v3 is far from lightweight. It can require substantial computational resources. In contrast, Mobilenets were developed with a mobile-first approach, leading them to be considerably smaller in size and therefore more efficient for mobile devices. The Mobilenet architecture leverages depthwise separable convolutions, which break down the convolution process into two simpler operations, a depthwise convolution followed by a pointwise convolution. This reduction in computation allows Mobilenets to maintain a lower number of parameters, ranging from 0.5 million to around 4 million, while still achieving good accuracy levels, though slightly lesser than those of Inception v3. Now let's see how we can implement the loading of both Inception v3 and Mobilenet models in our Android application using TensorFlow Lite. In the provided code, we create two instances of the interpreter class, which is essential for running our TensorFlow Lite models. The first line initializes the Inception interpreter, using the load model file function with the file path to the Inception v3 model, Inception v3 tflight. This allows the interpreter to access the model file stored on the device, enabling us to leverage the capabilities of Inception v3 for tasks that require high accuracy. Next, we introduce the Mobilenet interpreter similarly, pointing it to the Mobilenet v1 tflight file. Through this method, we ensure that both models can operate within our application, allowing for flexibility depending on the specific needs of our tasks. The ability to switch between a high-accuracy model and a more efficient one demonstrates the contrast between computational demands and performance, key factors to consider when developing mobile applications. This code snippet is crucial for enabling model inference and further manipulations in our project, paving the way for effective integration into our app. Now let's implement the following code to benchmark both the Inception v3 and Mobilenet models, allowing us to compare their performance directly. The first part of the code defines the parameters for the Inception v3 model, where we specify the path to the model file, the input layer's name, its expected input shape, and the output layer we want to evaluate. This structured configuration is crucial for the benchmarking process to correctly interpret the model's specifications. Next, we call the runBenchmark function, which executes the defined parameters to measure the Inception v3 model's performance on the specified device. After assessing Inception v3, we move on to the Mobilenet model. Again, we set up its parameters, including the model's file path and input configuration, tailored for Mobilenet's unique architecture. This step is essential as it enables us to utilize the lightweight nature of Mobilenet while still measuring its effectiveness. By executing the benchmark for both models, we gather valuable insights into their respective performance metrics, helping developers make informed choices based on the application's requirements, particularly weighing speed against accuracy. However, while speed is essential, accuracy should never be overlooked. If your primary goal is to achieve the highest possible accuracy for complex image classification tasks, Inception v3 should be favored despite its performance cost. Its intricately designed architecture helps extract valuable features that are crucial in better differentiating between visually similar classes. To further clarify, let's extend our understanding of accuracy by reviewing a scenario where Inception v3 shines versus where Mobilenet might still suffice. For projects involving the classification of medical images, where accuracy can profoundly affect outcomes, Inception v3 is likely the better choice. In contrast, for applications that assess everyday objects, such as identifying common household items, Mobilenet can provide a remarkable trade-off with efficient processing. Now let's see how we can implement the retraining of a Mobilenet model using TensorFlow's provided tools. The command we will be using starts with Python TensorFlow /examples/image retraining/retrain, py, which specifies the script we are executing to perform the retraining. Following that, we define important flags that guide the process. The output graph flag indicates where to save the newly trained model file, allowing us to customize the name and location of the output. Similarly, the output labels flag specifies the path for the labels file that will correspond to the retrained model, enabling proper labeling of the predictions made by the model. Next, we set the image dir to the directory on our system that contains the images we will use for training. This is crucial, as the quality and variety of images can significantly impact the retraining results. Lastly, the architecture is defined via the architecture flag, where we choose Mobilenet 1.0.224. This specific architecture provides a good balance of performance and model size, making it suitable for mobile applications that require both speed and accuracy. With this setup in place, you can fine-tune your Mobilenet model effectively. In selecting a model for current applications, developers must weigh the pros and cons of these two options in relation to specific use cases. If the application heavily relies on accuracy and can tolerate slightly slower performance, Inception v3 fits best. Yet if the need is for rapid execution with reasonable accuracy, Mobilenet is often the more appropriate choice. Moreover, consider not only the objectives of your mobile application, but also the devices on which you'll deploy your models. Picking models that match your target devices can significantly influence the performance users experience. Thus, ensure to benchmark and adjust your strategies based on direct performance tests, as demonstrated earlier. As we reach the end of our exploration regarding these two powerful models, we've covered quite a spectrum. We learned that while Inception v3 is preferred for accuracy and intricate feature extraction, Mobilenet offers superior efficiency and speed for mobile implementations. The choice between the two should be dictated by the intended application and the operational constraints it faces in real-world scenarios. Both models can be easily integrated into Android and iOS applications equipped with TensorFlow Lite, and effective benchmarking can help you refine your choices further. So whether you're building an app for fun or a more serious endeavor, understanding these options will empower you to deliver the best experience for your users. The world of mobile machine learning is evolving rapidly, and understanding the distinctions between models like Inception v3 and Mobilenet is crucial for developers aiming to deploy efficient applications on mobile devices. Today, we're diving into how these two models stack up against each other and which one you should choose for your particular use case. So far, we learned about the differences between Inception v3 and Mobilenet models, emphasizing the importance of selecting the right model based on specific application requirements. Inception v3 offers high accuracy with its complex architecture, but demands significant computational resources, making it suitable for tasks needing precise image classification. Conversely, Mobilenet is optimized for mobile devices with smaller size and faster inference times, providing a good balance of speed and accuracy for applications like real-time image recognition. Developers must consider their project's goals and target devices to effectively utilize these models. Now let's see how we can build the benchmark model utility provided by TensorFlow to evaluate the performance of the Inception v3 model. To initiate this process, we use the command bazelbuild-copt tensorflow/tools/benchmark benchmark model, which compiles the benchmark model tool. This line ensures that we are using optimized code, which is crucial to obtaining accurate performance metrics. Next, we will write the command needed to run the benchmark against our Inception v3 model. The command specifies several important parameters: the graph file containing the model weights, the input layer and its shape, the data type of the input, the output layer, and various flags controlling what information is displayed during the run. By configuring these options, we can control the level of detail in the output, such as whether to show run order or timing data. When executed, this command calculates and displays the floating point operations per second, flops, required for inference, giving us a clear understanding of the computational demands of our model. This insight is vital for optimizing performance on specific devices, especially those with limited resources. Now let's see how we can implement the benchmark test for the Mobilenet model. The command you will use is similar to the one for Inception v3, but with a key modification to the graph file path. This command specifies the location of the Mobilenet graph file, which you should have trained previously. The input layer shape, and input layer type parameters define the input characteristics expected by the model, with the input layer set to mul and shaped for images of size 224 x 224 pixels with 3 color channels. In this setup, the output layer identifies which layer of the model you want to evaluate. In this case, it's set to final result, which holds the classification output. The flags show run order, show time, and show memory are all set to false to streamline the output, allowing you to focus solely on the performance summary generated by the flag show summary, which provides essential information like the floating point operations per second, flops. Executing this command will help you assess how efficiently the Mobilenet model can make inferences, revealing its potential for real-time processing applications. Now let's implement the following command to retrain a Mobilenet model using TensorFlow. This command is crucial as it prepares the model for tasks specific to your dataset. Here, we begin by defining the output graph and labels, specifying where the retrained model will be saved. The output graph file is designated to save the model's architecture and weights, ensuring that it can be loaded later for inference. Moving on, we specify the output labels file, which will contain the names of the classes your Mobilenet model has been trained to recognize. The image dir parameter is also important, as it points to the directory storing your training images, directly influencing the quality of your retrained model. Furthermore, we've included the bottleneck dir to hold intermediate representations of your training images, which can speed up the retraining process significantly by reducing redundant computations. Lastly, the architecture flag indicates which version of Mobilenet we are using, in this case, Mobilenet 1.0.224. This version provides a balance of size and accuracy, making it well suited for mobile applications. Overall, this configuration allows for tailored retraining of the Mobilenet model to your specific use case, facilitating effective deployment in real-world applications. Now let's see how we can run predictions using our retrained Mobilenet model. We will use the label image utility provided by TensorFlow for this purpose. To start, we will execute a command that specifies the path to the graph file of our retrained Mobilenet model, which contains all the necessary components for making predictions. We also need to provide the path to the image we want to classify. In this case, it's an image of a dog located in the /tmp directory. The input layer and output layer are defined in the command, ensuring the model knows where to take data from and where to place its predictions. Additionally, we need to specify the input height and width, which must match the dimensions that the model was trained on, in our case, 224 by 224 pixels. By including parameters for input normalization, such as mean values and standard deviation, we help the model interpret the image data correctly. After executing this command, we'll receive an output that displays the model's classification results, showcasing predicted classes alongside their confidence levels. For example, among the predictions, we might see a Labrador Retriever with a high certainty score, reflecting the model's accuracy in categorization. This not only demonstrates the capabilities of the Mobilenet model, but also highlights the effectiveness of proper training and tuning for real-world applications. Another critical aspect to consider is the size of the models. While Inception v3 comes in at approximately 25 million parameters, Mobilenet is considerably lighter and comes with an architecture designed specifically for mobile devices. These models typically range from 0.47 million to 4.24 million parameters, making them suitable for environments with limited resources. Depending on the Mobilenet architecture variant you choose, like 1, 0.75, 0.5, or 0.25, you can tailor accuracy versus computational overhead further. But let's get even more technical. If you choose to quantize your Mobilenet model using the quantized suffix in your architecture value, you can greatly reduce your model size. A model such as Mobilenet 1, 0224 quantized results in a retrained model size of about 5.1 MB, an outstanding example of how Mobilenet aims to optimize not just speed but also resource usage. When considering deployment on actual devices, you should weigh the trade-offs carefully. For instance, if you're building an application where a few extra seconds in inference time is acceptable for very high accuracy, Inception v3 is the right choice. However, in scenarios like mobile-based augmented reality or even health-related applications that require real-time responses, Mobilenet stands out due to its lightweight nature and remarkable speed. You must thoroughly plan your deployment strategy, keeping in mind the devices on which your application will run. Newer devices are undoubtedly more powerful and can even take on models like Inception v3 with ease, but when you need operational efficiency across a variety of smartphones, Mobilenet is generally a better choice. Ultimately, the choice between Inception v3 and Mobilenet for mobile applications comes down to your specific needs. If you want the highest accuracy in your classification tasks and are willing to pay the price in terms of speed and resource usage, Inception v3 is the model for you. However, if your application demands quicker responses and uses less power, Mobilenet should undoubtedly be your pick. In summary, understanding these two models allows you to select the right architecture for your application. You want to decide based on accuracy requirements, speed constraints, and the capabilities of your target devices. As mobile technology continues to advance, so too will the models that help empower your applications. Stay informed, stay curious, and keep experimenting with these powerful tools. Thank you for following along in this session. We dived deep into the performance comparisons between Mobilenet and Inception models for mobile applications, explored practical implementation steps, and discussed when to use which model, ensuring you have a toolkit ready for your next mobile development challenge. Alright, let's dive into the fascinating realm of optimizing Mobilenet performance for inference speed. This module is crucial for anyone looking to implement deep learning models on mobile devices, where speed and efficiency are paramount. So far, we covered the differences between Inception v3 and Mobilenet, focusing on the balance between accuracy and speed tailored for mobile applications. Now we'll explore how to optimize Mobilenet's performance, particularly in terms of inference speed, giving you actionable insights to enhance your applications. To kick things off, it's essential to understand what inference speed actually means. Inference is the process where your trained model makes predictions or classifies an input based on what it learned during training. The inference speed indicates how swiftly this process can occur, which is particularly important for mobile applications that require real-time performance. You might have noticed that when switching from Inception v3 to Mobilenet, the flops estimate drops significantly. For instance, by replacing the benchmark model graph with the Mobilenet retrained model, DOG retrained Mobilenet 10224, PB, and running the benchmark tool, you could witness an intriguing reduction in flops from about 11.42 billion to roughly 1.14 billion. That's approximately 10 times faster. Now let's see how we can implement the retraining of the Mobilenet model using TensorFlow. The command starts with Python TensorFlow /examples /image retraining /retrain pi, which calls the retraining script designed to adjust the model based on your specific dataset. The output graph parameter specifies the file path where the retrained model will be saved, in this case, as dog retrained Mobilenet 10224 PB, providing you with the updated model for use in predictions. The output labels parameter designates where to save the labels corresponding to the retrained model, allowing you to easily reference which classes your model has learned. You'll also provide your image datasets directory with the image dir parameter, letting the retraining script access the images needed for the training process. The bottleneck dir option points to the directory where bottleneck files are stored, helping to optimize the retraining by reducing computational overhead. Finally, the architecture flag indicates which Mobilenet variant to use, and opting for Mobilenet 1.0.224 indicates a preference for the most comprehensive model, aiming for higher accuracy. This setup lays the groundwork for effective model optimization, striking a balance between performance and resource efficiency. Next, we will implement the quantization of the Mobilenet model to optimize its performance for mobile applications. This can be achieved by modifying the architecture parameter in our retraining command to include the quantized suffix. By specifying Mobilenet 1.0.224 quantized, we tell TensorFlow to perform quantization, which converts the model weights from float 32 precision to int 8 precision. This process significantly reduces the model size from approximately 17 MB to around 5.1 MB, which leads to quicker loading and faster inference times during execution. Additionally, the other parameters in the command remain the same. We still specify the output graph and labels, as well as the image directory and bottleneck directory, ensuring that the retraining process utilizes the appropriate paths and identifiers. Running this command will retrain the Mobilenet model while applying quantization, allowing it to operate efficiently on mobile devices. This step is crucial for enhancing inference speed, which is vital for real-time applications. Hence, by following this command structure, you set your model up for optimal performance while keeping resource usage minimal. Now that we have our Mobilenet model retrained and quantized, we need to test its functionality using TensorFlow's label image utility. This utility is crucial as it allows us to classify images and verify that our model is performing correctly. Next, we will implement a command that specifies the parameters necessary for the classification task. The graph parameter points to the retrained Mobilenet model file, which contains the architecture and weights of our model. For this example, we are using the model stored in dog retrained Mobilenet 10224 PB. We also specify the path to the input image using the image parameter, which in this case is lab1 JPG, located in the /tmp directory. Now let's discuss the input layer and output layer. The input layer parameter, designated as input, indicates the layer where the image data is fed into the model, while the output layer parameter, defined as final result, specifies where the classification results will be obtained. Additionally, we set the dimensions for the image with input height and input width, ensuring they align with the model's expectations, which are both set to 224 pixels. Finally, we establish the image preprocessing parameters using input mean and input std. These parameters, both set to 128, are vital for normalizing the input image to enhance the model's performance. Overall, this command will help us evaluate how well our retrained model classifies the input image, providing us valuable insights into its effectiveness. Now let's take a look at the output format generated after running our model to classify an image. The classification result consists of a list of labels corresponding to different dog breeds, each accompanied by a probability score that signifies the model's confidence in its prediction. For example, in the output, you'll notice entries like N020999712, Labrador Retriever 41, 0.824675. Here, the code specifies that the model predicts an 82.5% probability of the image being a Labrador Retriever, indicating a strong likelihood of accuracy. The numbers preceding the breed names represent the corresponding identifier in the label file, enabling further insights into the classification choices made by the model. Additionally, the subsequent entries indicate other potential classifications with their respective probabilities, such as N020996001 Golden Retriever 64, 0.144245, meaning there's a 14.4% chance that the image could be classified as a golden retriever. This output is pivotal as it not only reflects the model's predictive performance, but also needs careful consideration during evaluation, allowing for adjustments in model training or data collection processes based on these probability scores. A significant part of optimizing Mobilenet is also about understanding the architecture behind it. Unlike heavier models like Inception, Mobilenet utilizes depthwise separable convolutions, a unique design choice that allows for efficient processing. By splitting the convolution into two layers, a depthwise convolution and a pointwise convolution, the model operates on fewer computations without sacrificing much in terms of accuracy. To clarify, in a traditional convolution, all filters in each layer apply to every channel of the input. However, depthwise separable convolution applies a single filter per channel before recombining the inputs with pointwise convolutions. As a result, Mobilenet has significantly fewer parameters and lower computing requirements while still performing well on various tasks. Now let's implement the benchmark tool to assess our Mobilenet model's performance. First, we need to build the benchmarking tool using the Basel build system, specifying the optimized configuration for TensorFlow's benchmark model. This step compiles the necessary dependencies and gives us access to the benchmark tool, which is crucial for evaluating our model's capability in real-world scenarios. Next, we will run the benchmark tool against our newly retrained and quantized Mobilenet model. In this command, we specify the model graph file that contains the architecture and weights of our Mobilenet, specifically the retrained Mobilenet 10224 PB file. It's important to define the input layer and its shape, which in this case is a single image with dimensions of 224 by 224 pixels and 3 color channels. We also indicate the input data type as float and set the output layer to final result, which corresponds to the model's predictions. Additionally, we opt not to show the run order, time, or memory usage to keep the output focused on a summary of the model's performance metrics. Finally, by showing the summary, we can glean essential information such as the estimated floating point operations per second, flops, which ultimately helps in understanding our model's efficiency for mobile deployments. As we begin wrapping up, it's essential to reiterate the strategies we've covered to enhance Mobilenet performance for inference speed. Beginning with proper retraining and implementing quantization, you can reduce model size significantly, leading to faster inference times. Testing the model through the label image tool provides confidence in your implementation. And finally, benchmarking your model reveals its operational efficiency on devices. So to summarize what we've gone through, we've learned how to optimize Mobilenet for inference speed by retraining, quantizing, testing, and benchmarking the model. You should now possess a well-rounded understanding of optimizing Mobilenet for your mobile applications, striking that vital balance between speed and accuracy. This conclusion serves not just to remind you of the strategies we've discussed, but also to emphasize their importance in real-world applications. As mobile devices evolve, the need for efficient models capable of real-time processing becomes increasingly critical. Whether you're developing a mobile app or a larger deployment, using Mobilenet as part of your machine learning toolkit is a smart choice. Thank you for joining this tutorial, and happy. In today's lesson, we are diving into a crucial topic in deep learning applications, choosing Mobilenet for efficient inference speed. Mobilenet is not just a fancy name, it's a revolution in how we optimize model performance for mobile devices. Understanding why and when to use Mobilenet can significantly impact the speed and efficiency of your applications. So far, we learned about optimizing Mobilenet performance for inference speed, particularly for mobile applications where efficiency is key. We covered the differences with Inception v3, discussed the importance of inference speed, and explored retraining and quantization techniques to enhance model performance. Additionally, we detailed how to test the model's functionality and benchmark its efficiency. Finally, we emphasized the balance between speed and accuracy when deploying Mobilenet in real-world scenarios. Now we will talk about practical approaches to using Mobilenet, comparing its performance metrics, particularly flops, against other models, and dive deeper into the implementation aspects. When we talk about inference speed in deep learning, it's essential to understand what's at stake. Each model comes with its own specifications in terms of architecture, complexity, and size, which directly affects how quickly you can run predictions on your mobile device. For example, if we look at the previous benchmark of models, Inception v3, which is a much larger and more complex model, requires approximately 11.42 billion floating point operations, flops, to make a single inference. This means on a standard smartphone like an iPhone 6, it would take about 5 to 6 seconds just to complete one prediction. In contrast, when we replace the graph file with a Mobilenet model-based retrained model such as DOG Retrain Mobilenet 10224 PB and rerun our benchmark tool, the flops estimate drops dramatically to about 1.14 billion. That's about 10 times faster. Just imagine the speed of your application being that efficient. This difference is significant, especially for real-time applications where users expect rapid responses. Now let's implement the following code to set up our Mobilenet model for classification tasks. First, we import TensorFlow and the Mobilenet architecture from Kira's applications, allowing us to access a pre-trained version that has learned features from the ImageNet dataset. By specifying weights equals ImageNet and include top equals false, we load the model without its original classification layers, enabling us to customize the top layers according to our specific classification objectives. Next, we define the input shape as 224, which corresponds to the expected size of the input images. After loading the base model, we obtain its output and proceed to add our custom layers. A global average pooling layer is included to ensure that the model effectively summarizes the spatial features extracted by Mobilenet. We follow this with a dropout layer set at 50% to help mitigate overfitting during training, particularly when applying the model to smaller datasets. Finally, we add a dense layer with a sigmoid activation function for binary classification tasks, defining our model's output. By tying everything together in the final model, we can now leverage Mobilenet's architecture as a powerful backbone for our classification needs. After building our Mobilenet model, the next step is to retrain it using our specific dataset to optimize its performance. Now let's implement the following command, which invokes the TensorFlow retraining script. This command allows us to specify important parameters, such as the output graph file where the retrained model will be saved, and the output labels file that lists the classes for our dataset. The image dir parameter points to the directory containing the images we will use for retraining, which is crucial for guiding the model during the process. Additionally, we specify a bottleneck dir, which is where the intermediate outputs from the model's calculations are stored, helping to speed up the retraining process. The architecture flag, architecture Mobilenet 10224, indicates that we are using the full Mobilenet model with an input size suitable for our images, ensuring that the model fits our training data's requirements. By retraining the model this way, we can gather optimized weights tailored specifically for the classes we aim to recognize, enhancing both the model's accuracy and its inference speed. Now let's see how we can benchmark the performance of our retrained Mobilenet model. The command provided is meant to run a benchmark tool specifically designed for TensorFlow models. By executing this command, we assess critical performance metrics including speed, memory usage, and flops, which are essential for understanding how well our model will perform in a real-world scenario. In the command, we specify the path to our trained model graph file, which holds the retrained weights and structure of Mobilenet. We also define the input layer characteristics, such as its name, shape, and data type, which tells the benchmarking tool how to properly feed data through the model. The output layer is likewise defined so that the tool knows where to capture the results. The flags used in this command allow us to customize the output. For instance, we can choose not to display run order, time, or memory details during benchmark execution, but ensure a summary is included to give us an overall picture of the model's performance. This step is crucial for confirming that our model is not only operational but also optimized for rapid inference, especially important in mobile applications where user experience is paramount. Now let's see how we can implement the quantization of our Mobilenet model to enhance its efficiency for mobile deployment. By appending quantize to our architecture specification, we instruct the retraining process to optimize the model not just for accuracy, but also for performance by reducing the numerical precision from 32-bit floating point to 8-bit integers. This significant change can lead to faster inference speeds and decreased memory usage, making the model much lighter and better suited for mobile devices. When we modify the architecture string in our retraining command, it indicates that we want our model to undergo quantization. This process is vital when targeting environments with limited computational resources, as it allows us to maintain a balance between model performance and inference speed. The The quantized model benefits from reduced model size and faster execution, which is crucial when deploying applications that require immediate responses. This simple adjustment can yield substantial improvements in the practical usability of our Mobilenet model, making it a powerful approach for real-world machine learning applications. Now let's see how we can implement a practical example of testing our Mobilenet model with the following code snippet. This implementation begins by loading the trained Mobilenet model stored in a specified path using TensorFlow's Keras API. It's essential to ensure that the path reflects where your retrained model file is saved. Next, we need to preprocess the input image before passing it to the model for prediction. The image is loaded from a designated file path, and its size is adjusted to match the input requirements of Mobilenet, in this case, 224 by 224 pixels. We convert this image into an array format suitable for model input. This is done using TensorFlow's image processing utilities, which not only resize the image, but also convert it into a numerical array. Finally, we expand the dimensions of the input array to include a batch-sized dimension, which is required for prediction. With the input ready, we utilize the model's predict method to obtain the model's predictions on this processed image. The predictions are then printed out, allowing us to evaluate how well the model recognizes or classifies the input data. This step is vital for verifying and analyzing model outputs in real-world applications. In conclusion, understanding how to efficiently use Mobilenet for deep learning applications allows developers to gain significant advantages in speed and performance, especially on mobile devices. The reduction in flops when switching from traditional models like Inception v3 to Mobilenet is profound and showcases how modern designs are tailored for today's technology landscape. As we wrap up this lesson, remember that positioning Mobilenet offers a great trade-off between rapid inference and satisfactory accuracy. It's essential to consider your application's needs, the capabilities of your end-user devices, and ultimately optimize accordingly. Now that you have a toolkit and process for implementing Mobilenet in your applications, go ahead and experiment with it. You'll see just how powerful this approach can be in real-world scenarios. Thank you for joining me today. Make sure to practice these implementations, and I look forward to diving deeper into more advanced topics in our next. In today's session, we are diving into an exciting topic: speed optimizations for Mobilenet models. We will explore how we can significantly enhance the inference speed by leveraging some techniques and nuances of the Mobilenet architecture. So far, we learned about optimizing Mobilenet for efficient inference speed, particularly in mobile applications. We contrasted its performance with Inception v3, exploring retraining and quantization techniques to enhance model efficiency. Additionally, we covered how to test the model's performance through benchmarking tools, emphasizing the importance of balancing speed and accuracy. Finally, we discussed practical implementations and adjustments for various applications, setting the stage for a deeper exploration today. Now we will discuss specific strategies to optimize the Mobilenet models for speed. One effective tactic involves altering the graph file by replacing it with the retrained Mobilenet model, like our dog retrained Mobilenet 10224 PB. By doing so, you can run the benchmark tool and witness that the flops estimate spikes to approximately 1.14 billion, making it about 10 times faster than previously recorded. This example perfectly highlights the impact of using fine-tuned models instead of baseline architectures. Now let's see how we can implement the Mobilenet model using TensorFlow for our custom dataset. First, we load the pre-trained Mobilenet v2 model, setting the input shape to 224 by 224 pixels with 3 color channels, while excluding the top classification layer. This allows us to leverage the powerful feature extraction capabilities of Mobilenet without the original output layer that corresponds to the ImageNet dataset. Next, we freeze the base model's weights to prevent them from being updated during training, ensuring that the learned features remain intact. Moving forward, we construct a sequential model by adding our base model followed by a global average pooling layer, which reduces the dimensionality of the output. Finally, we add a dense layer configured with 10 units and a softmax activation function, suitable for our specific classification task involving 10 classes. Once the model architecture is defined, we compile the model using the Atom optimizer, the sparse categorical cross-entropy loss function, and accuracy as our evaluation metric. In the last step, we fit the model to our training dataset while also validating it against a separate validation dataset over 5 epochs, which allows our model to learn from the new data effectively while maintaining its ability to generalize. Now let's implement the quantization of our retrained Mobilenet model to enhance its performance on mobile and edge devices. The first step is to create a TensorFlow-like converter using our Keras model, which will facilitate the conversion process. We set the converter's optimizations to include default settings, allowing TensorFlow to automatically select appropriate quantization techniques. This adjustment aims to reduce the model size and improve inference speed by converting the model's weights from a higher floating point precision to INT8 representation. Once we've configured the converter, we invoke the convert method to generate a TensorFlow-Lite (TF-Lite) model that embodies these optimizations. This lightweight model is better suited for execution in resource-constrained environments, delivering faster inference times. Finally, we save this quantized model to a TF-Lite file. By writing the model to disk, we can easily deploy it to mobile applications, ensuring it runs efficiently on devices with limited computational power while still maintaining respectable performance levels. This implementation is a critical step in making our machine learning solutions viable for practical, real-world applications. Now let's implement the pruning technique to further optimize our Mobilenet model. We begin by importing necessary libraries from TensorFlow's model optimization toolkit, specifically focusing on sparsity functions. Next, we set up a pruning schedule that manages how the model's weights will be pruned over time. The initial sparsity parameter starts at 0, indicating no weights will be pruned at the beginning of the training process. Gradually, we aim to reach a final sparsity of 0.5, meaning half of the weights will be eliminated by the end of the pruning period. The begin step and end step indicate when this pruning should commence and conclude, creating a structured approach to weight reduction. The frequency parameter specifies how often pruning occurs during the training. Once the pruning schedule is defined, we apply it to our existing model using the prune low magnitude function. This enhances the model's efficiency by reducing the number of parameters, which translates to faster inference times. After refining the model with pruning, we compile it again with the atom optimizer and a loss function suited for sparse categorical output. Finally, we fit the newly pruned model on our training dataset while validating on a separate validation dataset, reinforcing its learning and adaptation to the task at hand. Now let's take a look at how we can effectively preprocess our images to optimize them for speed in Mobilenet. We begin by importing the image data generator class from TensorFlow's Keras API, which is essential for loading and augmenting image data. Here, we define a data generator that rescales the pixel values from the range of 0, 255 to 0, 1 by applying a simple rescaling factor of 1,255. This normalization step is crucial as it helps the model learn more effectively by standardizing the input data. Next, we set up the flowFromDirectory method to load images from a specified directory. This method allows us to feed images directly into our model while applying the adjustments defined earlier. We specify the target size parameter to resize our images to 160. This new size ensures our model operates efficiently and increases throughput without significantly impacting accuracy. Additionally, we configure the batch size parameter to 32, which determines how many samples will be processed at once during training, balancing memory usage and speed. The class mode is set to sparse, which is suitable for multi-class classification problems where labels may not be one-hot encoded. By implementing these settings, we prepare our dataset for optimized training and inference with the Mobilenet model. In conclusion, optimizing Mobilenet models for speed is quintessential in making them viable for mobile and edge applications. We explored retraining with specific datasets, quantization for efficiency, pruning to reduce model size, and balancing input dimensions for maximum throughput. Each of these elements plays a crucial role in enhancing the inference speed while maintaining a good level of accuracy. As you move forward, consider experimenting with these techniques at your convenience and fine-tune them as necessary according to your application requirements. With the ever-growing importance of mobile computing, your efforts in optimizing models can bring about significant improvements in experience for the end user. Thank you for joining me today. Stay tuned for upcoming lessons where we will put these optimizations into practice. Whether you're developing for iOS or Android, all of these strategies can be adapted accordingly to deliver efficient applications powered by superb machine learning models. See you next. In June 2017, Google took a significant step by releasing Mobilenets v1, a collection of 16 mobile-friendly deep learning models specifically designed for TensorFlow. These models allow developers to efficiently deploy deep learning solutions on mobile and edge devices, balancing performance with power consumption. In today's lesson, we will delve into the process of retraining Mobilenets for custom image recognition tasks. So far, we learned about optimizing Mobilenet models for improved inference speed. Now, we will cover how to leverage Mobilenet models to create a custom image classifier by retraining them effectively. Now let's take a look at how to structure your dataset for the Mobilenet model retraining process. As we discussed earlier, for the model to effectively learn, you need to organize your images into separate folders based on their respective classes. The directory structure shown in the example illustrates this organization clearly, with distinct folders for dogs and cats, each containing various images. This setup allows the retrain script to efficiently locate and process the images during training. Next, we will write the command to initiate the retraining process using the TensorFlow library. By calling the retrain script, we specify several important parameters: the output graph where the retrained model will be saved, the location for the output labels, and the image directory that points to our previously organized dataset. Additionally, it's vital to define the bottleneck directory to store the precomputed features that significantly expedite training. Lastly, we will choose the architecture of our Mobilenet model. Here, we opt for Mobilenet 1.0.224, which balances performance and resource usage nicely. This command sets the foundation for customizing the Mobilenet model to effectively classify the images in our dataset. Now let's see how we can implement a test command to evaluate the performance of our retrained Mobilenet model. This command utilizes the label image tool from TensorFlow, allowing us to classify images using our newly trained model. We start by specifying the path to the graph file, which contains the structure and weights of our model, ensuring it knows how to interpret input images appropriately. Next, we provide the location of the test image, which is the file we want the model to classify. It's important to input the correct height and width for the image processing to align with the dimensions used during model training, which is set to 224 pixels in both directions. Additionally, we specify the layers for input and output, clearly indicating the initial point of data feeding into the model and how we desire the final results to be presented. To enhance the model's understanding, we also define the mean and standard deviation values, which help standardize the input data. By following these steps, you can effectively assess how well your model performs on unseen data, giving insights into its accuracy and potential areas for improvement. Now let's see how we can evaluate the performance of our retrained Mobilenet model using a benchmark tool. The first step involves building the benchmark model using Bazel, a build tool. The command initiates the build process with optimization flags to ensure our model runs efficiently. Once the build process completes, we execute the benchmark model, specifying several important parameters for our analysis. We need to provide the path to the retrained model's graph, which is crucial for the benchmarking process. In addition, we define the input layer properties, including its shape and type, which in this case is a floating point format suitable for our model's architecture. We also indicate the output layer, which delivers the final classification results. Options are available to modify the output display settings, such as whether to show timing and memory usage. However, we have opted to focus on providing a summary of the results. By running this command, we will receive vital insights on floating point operations per second, flops necessary for inference, which are particularly beneficial for assessing the model's compatibility with mobile devices and performance efficiency in real-time applications. Now let's implement data augmentation to enhance our dataset and improve the robustness of our model. We will utilize the image data generator class from Keras, which provides various image transformation capabilities to artificially expand our training dataset through random alterations. First, we initialize the image data generator instance with specific parameters that dictate the nature of the transformations. For instance, we set the rotation range to 40 degrees, allowing the images to be randomly rotated within that range, which helps the model learn to recognize objects from different angles. Additionally, the width shift range and height shift range parameters introduce shifts along the width and height axes, respectively, enabling the model to familiarize itself with various object positions in the images. Moreover, shear transformations, zooming capabilities, and horizontal flips are included to further diversify the dataset. The fill mode is set to nearest, which fills in any pixels that might be created due to the transformations by using the nearest pixel values. Finally, once the parameters are established, we call the fit, method on our training dataset Xtrain, allowing the generator to compute the necessary statistics. This augmentation process is critical in ensuring that the model generalizes well to unseen data by exposing it to a wider variety of image scenarios. In summary, retraining Mobilenet models for custom image recognition tasks is a powerful approach that leverages the efficiency of their design. Through understanding the architecture, using the retrain, script, and benchmarking your results, you can create custom solutions tailored to specific use cases. From data organization to deploying models on devices, each step contributes to a robust image recognition system that can perform effectively on mobile platforms. Now that we've investigated how to train and leverage Mobilenets for custom image recognition, get ready to dive deeper into practical implementations and techniques in deploying these models into production settings seamlessly. In June 2017, Google released Mobilenets v1, delivering a groundbreaking suite of mobile-first deep learning models designed for efficient image recognition tasks. These models not only facilitate image classification, but are also lightweight, making them highly adaptable for mobile and embedded applications. Today, we will dive deeper into the Mobilenet architecture and learn to implement them in real-world scenarios, leveraging their capabilities to build efficient machine learning applications. Now let's implement the necessary steps to use Mobilenet in our project. First, we need to ensure that TensorFlow is installed in your environment, which provides the core library that facilitates the development and execution of machine learning models. Once everything is set up, we'll import various essential libraries. The import statements bring in TensorFlow, the Mobilenet model, and utilities for image preprocessing and decoding predictions, along with NumPy for handling arrays. These components are crucial for working with images and enabling us to utilize the Mobilenet architecture effectively. Next, we can proceed to load the pre-trained Mobilenet model, which has been trained on the ImageNet dataset. This provides a strong foundation for classifying images with minimal additional training. Following that, we will load and pre-process an image for classification. It's important that the image is resized to the required dimensions of 224 x 224 pixels before converting it into an array. By expanding the dimensions of the image array, we prepare it for batch processing, and applying the Mobilenet-specific preprocessing allows the model to interpret the image accurately. With this setup, we are ready to classify images using the model. Now let's see how we can implement the predictions using our pre-trained Mobilenet model. First, we utilize the model's predict method to generate predictions based on the preprocessed image array we created earlier. The output of this method is a set of probabilities corresponding to different classes from the ImageNet dataset. To make sense of these predictions, we then employ the decode predictions function, which transforms the raw prediction output into a more interpretable format, showcasing the most likely classes and their respective scores. Afterward, we prepare to present our results in a clear manner by iterating through the top 3 predictions. In this loop, we extract the label, probability score, and the corresponding ImageNet ID for each prediction. Finally, we format and print these results, displaying the class label along with its confidence score, which tells us the likelihood that the image belongs to that specific class. This straightforward approach not only demonstrates the ease of using Mobilenets, but also enriches your understanding of handling predictions in image classification tasks. Now let's implement the command to test our retrained Mobilenet model using the labelImage utility. This command is designed to validate whether the model can accurately differentiate between the dog breeds it has been trained on. We start by specifying the graph file, which is the retrained model saved earlier, making sure it points to the correct path of the model file. Next, we will set the path to the image we want to classify. Remember to replace the placeholder with the actual image you wish to analyze. Moreover, we need to define the input and output layers of the model. The input layer is where the data is fed into the model, while the output layer indicates where to find the prediction results. Additionally, it's essential to specify the expected dimensions of the input image by indicating the height and width, which should be 224 pixels for Mobilenet. The last parameters adjust the input image's mean and standard deviation, which normalize the input data to align with what the model expects. Upon execution, you will receive results that indicate how well the model can classify the specified dog breed, showcasing its performance in real-world scenarios. Now let's implement the benchmark model using TensorFlow to evaluate the performance of our retrained Mobilenet. First, we need to build the benchmark tool, which is essential for assessing the model's efficiency. By executing the build command, we compile the necessary files for the benchmark model, enabling us to run performance tests on our trained model. Next, we will run the benchmark against our specific Mobilenet model. In this command, we explicitly specify the graph file that contains the retrained Mobilenet model, along with the details of the input layer and its properties. The input layer is defined as mul with a shape suitable for Mobilenet's expected dimensions. By declaring the input layer type as float, we ensure that the model processes the input data correctly. Furthermore, we have options to manage the output layer settings and control the display of various metrics. By setting flags for runtime, memory usage, and summary display, we focus on obtaining useful insights like flops, floating point operations per second. This performance metric is crucial, as it indicates how efficiently our model can execute inference on resource-constrained devices, helping us optimize our application for mobile environments. As we wrap up our exploration of Mobilenet models, we have delved deep into their architecture, implementation, and retraining processes for practical image recognition tasks. We've seen how easy it is to classify images using pre-trained models and how to tailor these models to meet specific needs by retraining them on custom datasets. The use of Mobilenets revolutionizes the capability to employ advanced techniques of image recognition on everyday mobile devices while balancing performance and size. As an exercise, consider experimenting with different parameter sizes for your mobile model to determine the ideal balance of accuracy and computation for your specific application. Remember, efficiency is vital in mobile development, and every bit of optimization counts. So there you have it, you're now equipped with the knowledge and tools to implement Mobilenets effectively. Happy coding, and let your creativity drive the next great app in image recognition. In June 2017, Google introduced Mobilenets V1, a groundbreaking series of 16 mobile-first deep learning models designed specifically for TensorFlow. These models prioritize efficiency and accessibility, unlocking possibilities for powerful on-device image recognition. Now let's see how we can set up our Mobilenet model for image classification using TensorFlow. First, we import TensorFlow and Keras, which provides us with the necessary tools to build and train our model efficiently. We then initialize the pre-trained Mobilenet V2 model, setting include top equals false to exclude the final classification layers. This is crucial because it allows us to customize the model for our specific task, enabling fine-tuning on our dataset. Next, we construct a sequential model by stacking the base Mobilenet V2 model with additional layers. The global average pooling to D layer is added to downsample the feature maps, which helps in reducing the model size and complexity while retaining essential information. Finally, we introduce a dense layer with a softmax activation function to output predictions for our 10-class classification task. This configuration aligns perfectly with multi-class classification scenarios. Once the architecture is defined, we compile the model with the Atom optimizer and sparse categorical cross-entropy as the loss function. This prepares our model for training, setting the stage for effective learning from our dataset. This approach not only leverages the efficiency of Mobilenets, but also ensures that we have a robust framework ready for image classification tasks. Now let's see how we can implement the retraining process of the Mobilenet model using TensorFlow's retrain py script. This command serves as a foundation for fine-tuning the pre-trained Mobilenet model on your own dataset. First, you'll specify the output file paths for both the retrained model and the labels associated with your data. The output graph argument directs TensorFlow to save the retrained model at the specified path, while the output labels points to where the class labels will be stored. The image dir parameter is crucial as it indicates the directory containing the images you want to use for retraining, ensuring the model learns from your specific visual data. Additionally, by utilizing bottleneck dir, you're directing TensorFlow to save intermediate bottleneck feature representations, which can speed up the training process and enhance performance. Lastly, the architecture option lets you choose the desired version of Mobilenet, such as Mobilenet 1, 0, 224. This flexibility allows you to tailor the model to balance accuracy and efficiency based on your application's requirements. Now let's see how we can implement the benchmarking process for our retrained Mobilenet model. First, we need to build the benchmark tool provided by TensorFlow, which allows us to evaluate our model's performance across different devices. We do this by using the basal build command, specifying the optimization flag to ensure the tool is optimized for performance. Once the benchmark tool is built, we can execute it to assess our model's efficiency. The command to run the benchmark specifies the path to our retrained model as well as the input and output layer details. Notably, we define the input shape and type, which are crucial for the benchmark to correctly interpret the model's architecture. Additionally, we configure options to suppress runtime details such as memory and execution order, focusing instead on a summary of performance metrics. By executing this command, we can obtain valuable insights like the flops, floating point operations per second estimate. This measurement highlights the computational demands of our model, showcasing the efficiencies of Mobilenet compared to traditional models, ultimately confirming its efficacy in mobile applications where speed is essential. Now let's see how we can implement the loading and inference of our retrained Mobilenet model in an Android application. The code begins by initializing a TensorFlow Lite interpreter, which is a lightweight runtime used to execute machine learning models on mobile devices. This interpreter is crucial for interpreting the pre-trained TensorFlow model, allowing your application to make predictions based on input data. Next, we prepare the input array, structured as a four-dimensional float array to match the expected input shape of the model, which is typically batch size, height, width channels. In this case, we are working with a single image of size 224x224 and 3 color channels, RGB. For the output, we create a two-dimensional array to hold the model's predictions, assuming there are 10 possible classes for classification. Once the input and output arrays are set up, the core inference is executed using the tflight run method, which processes the input and generates the output. Finally, we use a post-processing step to determine which class the model predicts as the most likely through the use of an argmax function, enabling us to extract meaningful predictions from the model's output. This systematic approach ensures an efficient integration of the Mobilenet model into the Android application for real-time image analysis. Before we wrap this up, let's talk about the importance of fine-tuning based on user feedback. Iterative development driven by feedback can significantly refine your model's performance. Collecting user data while respecting privacy can help you refine your model's accuracy continuously. Regular updates ensure that your app remains efficient and relevant. In this lesson, we advanced our understanding of Mobilenets from architecture to deployment strategies. We analyzed retraining processes, explored benchmarking, and highlighted the importance of iterative modeling. By leveraging these insights, you can develop responsive, efficient mobile applications that harness the power of deep learning. To summarize what we've covered today, we delved into the efficient architecture of Mobilenets, learned about the process of retraining these models for specific datasets, used benchmarking tools to evaluate performance, and discussed the deployment of Mobilenet models in mobile applications. As we move forward, the next step is to explore how to integrate these models effectively into real-world applications. Mobilenet models are revolutionary in the realm of deep learning, particularly when it comes to mobile and edge devices. Today, we will dive deep into how Mobilenets can be utilized for fast inference speeds, enabling real-time applications that rely on image classification. By optimizing our models, we can achieve incredible performance while maintaining efficiency and responsiveness, which is crucial for mobile applications. So far, we learned that Mobilenets provide efficient deep learning models tailored for mobile devices, focusing on image classification. We examined their architecture, including depthwise separable convolutions, and explored the retraining process to adapt models to specific datasets. Additionally, we discussed performance benchmarking and the strategic deployment of Mobilenets within mobile applications. Moving forward, we'll explore effective integration of these models into real-world scenarios. In the previous lesson, we tapped into the Mobilenet architecture, highlighting its ability to run on limited hardware while delivering impressive accuracy in image classification. Now, let's discuss how to measure the efficiency of these models through benchmark tools and understand what makes Mobilenet suitable for rapid inference. A crucial aspect revolves around the floating point operations per second flops metric, an essential measurement of computational speed and efficiency. Now let's implement the code to load and benchmark our retrained Mobilenet model using TensorFlow Lite. We begin by importing the required libraries, TensorFlow for model handling and time for measuring inference duration. Next, we initialize the TensorFlow Lite interpreter by specifying the path to our Mobilenet model, enabling us to execute the model's operations efficiently on mobile devices. Once the interpreter is created, we allocate memory for the model's tensors, which is crucial for the model to function correctly. Following that, we retrieve the input and output tensor details, as understanding their shapes and indices is vital for preparing input data correctly. The input data must match the expected dimensions of the model, so we create a sample input array using random values that align with the input shape. Next, we set the sample input tensor into the interpreter and start timing the inference process. By invoking the model, we can capture the end time and calculate the time elapsed during this operation. Finally, we print the inference time, giving us valuable insights into the model's processing speed, a key performance metric for deploying efficient applications on mobile devices. Now let's discuss how we can effectively preprocess images for our Mobilenet model. We will write a function that prepares images to ensure they are suitable for input into our model. First, we load an image from the specified file path using the PIL library, which provides robust image processing capabilities. Once the image is loaded, it undergoes resizing to the dimensions of 224 x 224 pixels, conforming to the input requirements of the Mobilenet architecture. This resizing is crucial as it standardizes the input dimensions and ensures that the model can process the images correctly. Following the resizing, we convert the image into a NumPy array and normalize the pixel values by dividing by 255. This normalization step scales the pixel values to the range of 0 to 1, which is essential for effective model performance. We also explicitly cast the image data to the float32 type to match the expected input format of the model. Finally, we add a batch dimension using NP, expand dims, which reshapes the data to include an extra dimension for batch processing. This prepared image can then be fed into the Mobilenet model, ensuring that it receives correctly formatted data for generating predictions. Now let's see how we can interpret the predictions made by our Mobilenet model after running the inference. After invoking the model, we begin by retrieving the output tensor, which contains an array of classification probabilities corresponding to the classes the model has been trained on. This step is crucial, as it provides the raw data needed to determine which class the model predicts as the most likely. Next, by applying the function np argmax to the output tensor, we can identify the index of the highest probability. This index represents the predicted class that the model believes is the best match for the input image. It's important to note that this mechanism allows for a robust and definitive classification process. The output value is then printed, giving a clear indication of the predicted class. This streamlined approach ensures that developers can easily integrate these predictions into their applications, facilitating quick responses and enhancing user engagement. By leveraging this simple yet effective code snippet, we can effectively extract meaningful predictions from our Mobilenet model with ease. Now let's see how we can implement quantization to further optimize our Mobilenet model. In the code snippet, we start by utilizing the TF-Lite converter to transform our trained Keras model into a TensorFlow Lite format, which is essential for mobile deployment. To achieve quantization, we set the optimizations attribute of the converter to TF-Lite optimize default. This instructs the converter to apply the default optimization techniques, which include reducing the model's precision from floating point to integer representation. This transformation significantly decreases the model size and enhances inference speed, making it particularly advantageous for mobile devices with limited resources. Once the conversion process is complete, we save the quantized model as a TF-Lite file, allowing us to deploy it in production-level applications. This step emphasizes the importance of efficient storage and faster execution, crucial elements in mobile app development. By benchmarking our quantized model, we can expect to observe improved performance metrics, reaffirming the benefits of quantization in making Mobilenets an excellent choice for real-time applications. Now let's implement the following Java class to encapsulate the TensorFlow Lite interpreter for our Mobilenet model. The model interpreter class is designed to simplify the model's interaction within our Android application. In the constructor, we attempt to initialize the interpreter instance with the provided model path. If the model loading encounters any issues, we ensure to print the stack trace, which aids in debugging. Next, we define a method named classify, which takes a two-dimensional float array as input, representing the data we want to classify. This method initializes an output array, sized according to the number of classes our model can predict, indicated by a placeholder numClasses. After preparing the input, we call the run method of the interpreter, passing in our input data and output array. This process runs the inference, and once completed, we return the first element of the output array, which contains the probabilities for each class. Through this structured approach, developers can efficiently integrate Mobilenet's deep learning capabilities into their applications while ensuring ease of use and optimal interaction with the TensorFlow Lite framework. In conclusion, by leveraging the Mobilenet architecture, we open up a domain of possibilities for mobile app development based on deep learning. With fast inference speeds and efficient model performance, developers can create applications that are not only responsive, but also capable of handling complex tasks, such as image recognition. Today, we learned how to benchmark our models effectively, pre-process images for optimal input, interpret model outputs, and utilize quantization to heighten performance. As you move forward, experiment with various datasets and adjust your Mobilenet configurations to find the best fit for your application's requirements. Remember, the key is to keep your models efficient and ready for the demands of themable language. Mobilenets have become a cornerstone in the realm of mobile-first deep learning applications. With efficiency at their core, these models not only maintain an impressive level of accuracy, but are also designed specifically for TensorFlow. In June 2017, Google unveiled Mobilenets V1, which consists of a remarkable 16 different models tailored for varying levels of performance and resource constraints in mobile devices. Now let's take a look at how to implement Mobilenet V2 in a TensorFlow application. We begin by importing the TensorFlow library, which is essential for utilizing its powerful machine learning capabilities. The first step in our code is to load the Mobilenet V2 model, pre-trained on the ImageNet dataset. This model is set to accept images with a resolution of 224 x 224 pixels, which is the standard size expected by Mobilenet. Next, we define a helper function called preprocessImage. This function is crucial for preparing images for predictions. It takes in the path to an image, loads it, and resizes it to 224 x 224 pixels. Additionally, it converts the image to an array format suitable for input into the model and applies Mobilenet's specific preprocessing steps to ensure compatibility. After that, we implement the predictImage function. This function calls our preprocessImage to prepare the image and then uses the loaded model to generate predictions. The predictions are decoded to provide the top 5 class labels with their corresponding probabilities, making it easy to understand the model's output. Finally, we include an example that demonstrates how to use the predictImage function with a specified image path, showcasing how seamlessly we can integrate Mobilenet into our applications. Next, we will look at how to load a smaller variant of the Mobilenet model for applications where speed is essential. In the code, we utilize TensorFlow's Keras API to load the Mobilenet V2 model, specifically choosing the weights pre-trained on the ImageNet dataset for better accuracy in classification tasks. By setting the input shape parameter to 224, 3, we prepare the model to accept input images that are 224 by 224 pixels with 3 color channels, RGB. We also introduce the alpha parameter, which determines the model's width. By setting alpha equals 0, 25, we opt for a smaller model, reducing the number of filters in each layer. This not only minimizes the overall model size, but also enhances inference speed, making it particularly well-suited for low-resource devices. This flexibility allows developers to select the most appropriate model variant based on their application's requirements, effectively balancing performance and efficiency. Now let's see how we can quantize a pre-trained Mobilenet model using TensorFlow. First, we start by importing the necessary libraries, including TensorFlow and the TensorFlow Model Optimization Toolkit. With the Model Optimization Toolkit, we can effectively reduce the model's computational requirements and memory footprint, making it more suitable for mobile devices. Next, we load the existing Mobilenet V2 model, which is pre-trained on the ImageNet dataset. This serves as the basis for our quantization process. The TF Lite converter is then instantiated from the loaded model, enabling us to convert it into a TensorFlow Lite format by setting the optimization flag to TF Lite Optimize. Default, we apply a series of default optimizations, including the quantization step that converts the model's weights from floating point to integer format. This significantly reduces the model size while maintaining performance. Finally, we save the quantized model as a tflight file, which can now be deployed on mobile and edge devices. This conversion not only facilitates faster inference times, but also diminishes storage requirements, creating a more efficient application that maintains a seamless user experience. Now let's take a look at how to create a TensorFlow Lite (TF Lite) model interpreter in an Android application. The code begins by importing the necessary TensorFlow Lite interpreter class, which allows us to run inference on our model. Inside the TF Lite model class, the constructor takes a model path parameter, which specifies the location of the quantized model. This is essential as it directs the interpreter to load the model into memory. Next, we have the load model file method, where we open the model file from the app's assets using an asset file descriptor. This method is critical in mapping the model file to a read-only memory buffer, enabling us to access it efficiently. By utilizing file input stream and file channel, we extract the required file's offset and length, ensuring the model loads correctly. Finally, the classify method takes a 2D float array as input and prepares an output array to hold the results. This method calls the interpreter's run function to execute inference, returning predictions based on the input data. This foundational structure allows developers to integrate advanced TensorFlow functionalities into their Android applications seamlessly. So far, we have learned about the architecture and various implementations of the Mobilenet models, including the advantages of using depthwise separable convolutions and the flexibility provided by different sized models. We've covered practical deployment strategies for quantized models, all within the context of TensorFlow and mobile-first applications. Now that you're equipped with a solid understanding of the Mobilenet architecture and how to integrate it into Android applications, the next step is to expand your reach by exploring more advanced use cases. This includes techniques like transfer learning with Mobilenets, potentially allowing you to create specialized models tailored to specific tasks or datasets while benefiting from the efficiencies Mobilenets provide. In conclusion, Mobilenets are not just about running models on mobile devices. They are about making deep learning accessible and efficient, opening the door to countless applications powered by AI right in the palm of your hand. Embracing these models means embracing the future of mobile AI, and you are now on the cutting edge of that revolution. Thank you for joining this deep dive into Mobilenets, and remember to keep experimenting and pushing the boundaries of what's possible with mobile deep. Mobilenets have become a significant player in the field of mobile-centric deep learning. Today, we're going to dive into retraining Mobilenet models for image recognition. This is a crucial step because it allows us to adapt pre-trained models to our specific tasks, all while enjoying the benefits of Mobilenet's efficiency. So far, we've learned about the significance of Mobilenets in mobile-first deep learning, highlighting their efficient architecture and depthwise separable convolutions. We've explored implementation details in TensorFlow, including quantization for enhanced performance on resource-constrained devices. Additionally, we discussed deployment strategies for integrating Mobilenets into both Android and iOS applications. Now we will cover how to retrain Mobilenet models to create specialized models tailored to specific tasks. To start, let's discuss what retraining a Mobilenet model means. Essentially, it involves taking a pre-trained Mobilenet model and fine-tuning it on a new dataset for a specific classification task. Google released Mobilenets v1 in June 2017, consisting of 16 mobile-first deep learning models optimized for TensorFlow, and these models are designed to run efficiently on devices that have limited computational resources. The models include a range of parameter sizes, from 0.25 million to 4.24 million, which enables us to strike a balance between speed and accuracy. While we can certainly build our models from scratch, using a pre-trained Mobilenet can significantly decrease the time to get started, saving us valuable resources. Imagine having a fully functional image recognition system while only needing to train it for a fraction of the time compared to building a model from the ground up. Now let's take a look at how to structure your dataset for retraining the Mobilenet model. It's essential to organize your images systematically, as this will allow the retraining script to access and process them effectively. In this case, you would create a directory for each class, such as dogs and cats, and place their respective images within these directories. This structured layout ensures that the model can learn from the appropriate examples during the training process. Next, we will implement the command that utilizes TensorFlow's retrain script to initiate the retraining process. The command includes several parameters. Output graph specifies the path where the fine-tuned model will be saved, while output labels defines where to store class labels. The image dir points to the location of our prepared dataset. Additionally, the bottleneck dier is crucial for storing intermediate bottleneck features that enhance retraining efficiency, and the architecture parameter allows us to choose the specific Mobilenet architecture we want to use. By setting it to Mobilenet 1, 224, we indicate that we prefer the full-sized model with a resolution of 224 x 224 pixels. This comprehensive command ensures that our training process is well organized and efficient. Now let's implement the command to test our retrained Mobilenet model using the label image tool. This command is designed to send an image file to our model, allowing us to retrieve the predicted label along with associated confidence scores. We start by specifying the path to our retrained model with the graph parameter, which should point to the PB file of the trained model we previously saved. Next, we specify the image we want to test using the image flag. Here, we reference an example image file located in a temporary directory. The input layer and output layer parameters identify the model's input and output layers, respectively, which are critical for the model's functioning. We also define the input dimensions with input height and input width, indicating that our model expects images resized to 224 x 224 pixels. Finally, the input mean and input STD flags help in normalizing the input image data for better accuracy during inference. Running this command will produce output showing the model's confidence in various possible labels, helping us evaluate its performance on the input image. Now let's see how we can enable quantization for our Mobilenet model during the retraining process. To achieve this, we need to modify the architecture parameter by appending quantized at the end, indicating that we want to create a quantized version of the Mobilenet model. This adjustment not only shrinks the model's file size significantly, from around 17 MB to 5.1 MB, but also optimizes it for performance on mobile devices, where storage and efficiency are essential. Next, we will write a command to build the benchmark model tool using Bazel. This step is crucial, as it prepares us to evaluate the performance of our retrained model. By compiling the necessary components with optimization flags, we ensure the benchmark tool runs efficiently. After successfully building the benchmark model, we can execute it to assess how well our quantized Mobilenet performs. The command we implement allows us to specify input and output layers along with shapes and types to match our quantized model architecture. This will give us valuable insights into computation requirements, measured in floating point operations, flops, helping us understand the trade-offs between model efficiency and computational intensity. In summary, we've covered a lot of ground today regarding retraining Mobilenet models for image recognition. We learned about the benefits of using pre-trained models, the structure of our data, and how to execute the retraining process using TensorFlow's tools. It's pretty impressive what you can accomplish with a few lines of code and a dataset. Now that you have the basics down, you can experiment with different datasets, architectures, and quantization modes to find the perfect balance for your image recognition tasks. Remember, the power of Mobilenets lies in their efficiency, which is particularly valuable in the mobile development landscape. So get out there, retrain some models, and let your applications do the heavy lifting with stunning performance. In this session, we are diving into the efficient retraining of the Mobilenet model for image recognition tasks. Mobilenets are designed specifically for mobile and edge devices, making them a go-to choice for those looking to implement deep learning without requiring substantial hardware resources. So far, we explored the significance of Mobilenets for mobile-centric deep learning, understood their architecture, and touched on the retraining process using TensorFlow. We also discussed the deployment of these models and the importance of quantization for improved performance. Now, we will cover how to optimize image recognition tasks further, cater to different datasets, and examine various Mobilenet architectures. Let's kick things off by talking about the advantages of using Mobilenet v1. Released by Google in June 2017, this model represents a total of 16 mobile-first deep learning architectures optimized for TensorFlow 4.0 source. With a size ranging from just a few megabytes, Mobilenets make it feasible to deploy machine learning applications directly on mobile devices with limited computational power. Now let's see how we can implement our organized dataset structure, which is crucial for effectively retraining our Mobilenet model. In this example, we have a folder named Images containing subfolders for each class, such as Labrador and Poodle. Each of these subfolders holds the respective images, ensuring a clean separation of data that the retraining process can leverage. Proper organization is paramount, as it helps the model to learn the features corresponding to different classes accurately. Next, we will write the command to execute TensorFlow's retrain script. This command specifies the output paths for the retrained model and labels, as well as where our images are stored and where the bottleneck files will be located. Notably, the architecture parameter is set to Mobilenet 1.0.224, indicating we are utilizing the full-sized Mobilenet architecture with an input image size of 224 x 224 pixels. This setup allows us to fine-tune the model effectively, balancing the trade-off between speed and accuracy based on the capabilities of the device being used. Now let's see how we can implement the label image tool to evaluate the performance of our retrained Mobilenet model. The command begins with the path to the label image executable, which is essential for classifying images based on the model we've just trained. After that, we specify the location of the graph file using the graph parameter, pointing to the saved retrained model. This tells the tool which model to use for predictions. Next, we define the input image with the image flag, allowing us to specify the exact image we want to classify. It's important to ensure that the image is compatible with the model's expectations in terms of size and format. We then set the input and output layer names with input layer and output layer, which are critical for directing the model to understand where to retrieve input data and where to place its predictions. Moreover, we define the dimensions of our input image through input height and input width, ensuring the image is resized appropriately for the model. The input mean and input std parameters adjust the image's pixel values to fit the model's training conditions, enhancing the accuracy of the predictions. Together, these components allow you to effectively test your model's image classification capabilities and obtain results that showcase its performance. Now let's see how we can benchmark our retrained Mobilenet model to evaluate its performance. First, we need to build the benchmark model tool using Bazel, specifying optimized compilation with the copt flag. This prepares the tool for efficient execution, allowing us to obtain precise performance metrics later on. Next, we will execute the benchmark against our retrained Mobilenet model or an Inception v3 model. In the command, we specify the path to the model graph, which is essential for the benchmarking process. Additionally, we identify the input layer and its shape, ensuring that it matches the configuration used during training. Setting the input layer type to float indicates the data format we are dealing with. Moreover, we designate the output layer and configure various flags to suppress unnecessary information during the benchmark run. By setting options like show run order, show time, and show memory to false, we streamline the output to focus on the summary of results. Finally, executing this benchmark will provide us insights into performance metrics such as flops, enabling us to compare inference times effectively between different models. As we conclude this section, let's summarize what we've covered. We explored how to efficiently retrain Mobilenet models for image recognition, emphasizing the preparation of datasets and the various command parameters necessary for executing retraining scripts. We also touched on quantization and how to evaluate model performance effectively. In our next session, we will dive deeper into further optimizations for Mobilenet architectures and investigate new approaches for adapting these models to unique datasets. We will also discuss practical tips for implementation on both Android and iOS platforms, ensuring you can seamlessly integrate powerful AI capabilities into your mobile applications. So make sure to stay tuned, as we will not only enhance our technical skills, but also unlock the potential of artificial intelligence on mobile devices. Don't hesitate to experiment with different datasets and try different architectures at home. The world of mobile deep learning is at your fingertips, and the possibilities are endless. Happy coding! In our exploration of deep learning models, we are diving into the effectiveness of Mobilenets aimed at efficient inference speed. Mobilenets are a family of lightweight models specifically designed for resource-constrained environments, particularly mobile devices. By optimizing these models for lower latency and quicker predictions, developers can enhance the user experience without sacrificing performance. So far, we learned about the importance of Mobilenets for efficient image recognition on mobile devices and the specifics of retraining these models using TensorFlow. We covered dataset preparation, various Mobilenet architectures, and how to implement quantization for optimized model size and performance. Additionally, we discussed testing model accuracy and benchmarking performance metrics. In the next section, we'll explore the practical implications of implementing the Mobilenet model and take a closer look at how to leverage its benefits for faster inference speed. To start, let's understand what we mean by inference speed. Inference speed refers to how quickly a model can process input data and generate predictions. For mobile applications, this speed is crucial, as users expect instantaneous responses. By replacing generic models with the Mobilenet architecture, we can achieve significant improvements in flops, floating point operations per second. In one particular case, using the retrained Mobilenet model, DOG retrained Mobilenet 10224 PB, benchmarks indicated an inference speed approximately 10 times faster than traditional models, with estimated flops around 1.14 billion. This drastic improvement allows for real-time applications in image recognition, augmented reality, and more. Now let's see how we can set up the TensorFlow Lite interpreter for our Mobilenet model in an Android environment. First, we initiate the interpreter by calling the interpreter class with the model file loaded through the loadModelFile method. This method is critical as it retrieves the tflight model file we've prepared previously from our retrained Mobilenet model, ensuring that it is ready for inference. We enclose our interpreter initialization in a try-catch block to capture any potential exceptions that may arise during this process. This is essential for smoother error handling, allowing us to debug more easily if the model fails to load for some reason, such as an incorrect file path or missing resources. By calling eprintStackTrace, we can log the error details, making it easier to identify and fix issues promptly. Once the interpreter is successfully initialized, we are set to execute the inference, paving the way for processing input images with our optimized Mobilenet model. This step is vital for efficient image recognition, which is the focus of harnessing Mobilenets in mobile applications. Now let's see how we can pre-process the input images to prepare them for the Mobilenet model. First, we retrieve the image from its file path using the Bitmap Factory's decodefile method, which reads the image and creates a bitmap object. To ensure the image meets the Mobilenet's input requirements, we resize it to standard resolution of 224 x 224 pixels using the bitmap createScaled bitmap method. This resizing ensures that the input dimensions align with what the model expects, as Mobilenet is optimized for this specific size. Next, we need to convert the resized bitmap image into a byte buffer, which is the format TensorFlow Lite uses to process the input during inference. We achieve this using a custom method, convertBitmap to byte buffer. In this method, we allocate a direct byte buffer with a size of 4 bytes per pixel for RGB multiplied by the total number of pixels, 224 x 224. The pixel values are retrieved and normalized to a range between 0 and 1 by dividing each color channel by 255. This normalization not only ensures the model can effectively interpret the pixel values, but also optimizes its inference efficiency. Thus, with the image properly pre-processed, we are ready for the model to perform inference. Now let's execute the model on the pre-processed input. First, we need to allocate an output array designed to hold the model's predictions. In the provided code, we declare a two-dimensional array called output, with its dimensions set to accommodate one sample and the number of classes predicted by the model, denoted by num classes. Next, we call the run method on our TensorFlow Lite interpreter, passing in the input buffer that contains our pre-processed image. This method processes the input and populates the output array with the predicted probabilities for each class. After executing the inference, it's crucial to assess these results. Now let's dive into logging the probabilities for the predicted classes. We accomplish this through a loop that iterates over each class index. Inside the loop, we log a descriptive message that displays the probability associated with each respective class, enabling us to evaluate the model's confidence in its predictions. This step is vital as it not only provides insights into the model's performance, but also forms the basis for potentially displaying the most probable class to end users in your application, enhancing user interaction and experience. Now let's implement model pruning to further optimize our Mobilenet for inference speed. In this section, we'll utilize the TensorFlow Model Optimization Toolkit, which provides tools to efficiently reduce the size of our models while maintaining acceptable accuracy. First, we start by loading the original model we have trained and saved in the H5 format. This is crucial as we will be applying pruning techniques directly to this model. Next, we apply the pruning method using tfmot sparsity, Kira's strip pruning model, which analyzes the model's parameters and removes those which have minimal impact on its output during inference. This step is essential in ensuring that our model becomes lighter and faster, enabling it to run more efficiently on mobile devices. Finally, after the pruning process, we save the updated model as my pruned model H5. This newly pruned model is then ready for redeployment on mobile devices, where it will significantly enhance inference speeds by reducing the overall computational workload. Pruning allows us to maintain a balance between model size and accuracy, paving the way for smoother user experiences in mobile applications. Now let's implement the following code to leverage the Neural Networks API and an API for increased performance on Android devices. By creating an instance of TensorFlow Lite options, we can modify the behavior of the TensorFlow Lite interpreter to take advantage of the mobile GPU. Specifically, we call the setUseNappyTrue method, which allows the interpreter to utilize specialized hardware for computations, rather than relying solely on the CPU. This is particularly beneficial for tasks that involve heavy processing, such as those often encountered in deep learning applications. After setting the NNAPI option, we create the interpreter instance, passing it the model file and the options we configured. This setup ensures that the interpreter will select the optimal computation path automatically, helping to significantly enhance inference speed. By implementing these configurations, we not only improve performance, but also align with best practices for utilizing the hardware capabilities of mobile devices effectively. Furthermore, this code snippet highlights the ease of integrating advanced features into your machine learning application, paving the way for smoother and faster user experiences. So now we have covered setting up Mobilenets for efficient inference speed, including loading the model, preprocessing images, executing inference, and enhancing performance with techniques like pruning and hardware acceleration. These methods collectively aim to improve the responsiveness required by mobile applications while leveraging powerful yet compact deep learning models. As we wrap up this section, it is crucial to remember the goal here is not just to accelerate model performance, but also ensure that your users do not notice any lag or delay in app responses. With Mobilenets combined with strategies we discussed, you're well equipped to achieve that balance of performance and efficiency. In future sessions, we'll dig into further optimizations and provide practical implementation tips to enhance your applications based on the lessons learned here. So, gear up and get ready for more insightful strategies. In this lesson, we're diving into the exciting world of retraining Mobilenets for fast and efficient image recognition. Mobilenets, developed by Google, revolutionized mobile deep learning applications by providing models that are not only lightweight but also capable of high accuracy. So far, we learned about the efficiency of Mobilenets for deep learning on mobile devices, focusing on optimizing inference speed through setup and preprocessing techniques. We explored how to load the Mobilenet model using TensorFlow Lite, prepare images for input, and execute the inference process, including capturing and interpreting output probabilities. Additionally, we discussed advanced optimization strategies such as model pruning and utilizing GPU support to further enhance performance. Now we will cover practical implementation tips, retraining strategies for Mobilenets, and how you can apply these techniques to boost your image recognition applications. Now let's implement the code to load and prepare our Mobilenet model with pre-trained weights. We start by importing the necessary libraries from TensorFlow, including the Mobilenet v1 architecture and the image data generator for data preprocessing. The first crucial step involves loading the Mobilenet model, specifying that we want to utilize the weights pre-trained on the ImageNet dataset and excluding the top layer, which allows us to customize our own classification layer later. Next, we freeze the base model to prevent its weights from being updated during the initial training phase. This is essential as it ensures that the established feature extraction capabilities of Mobilenet are retained while we train the newly added layers. Following this, we construct a sequential model that includes the base Mobilenet followed by a global average pooling layer, a dense layer with 256 neurons activated by RayLU, and finally, an output layer with 10 neurons activated by softmax, which corresponds to our classification task. This setup allows us to leverage the pre-trained features while adapting to our specific dataset for improved performance in image recognition tasks. Next, we will set up the compilation and training of our model by defining a loss function, optimizer, and performance metrics. First, we use the Atom optimizer, which is popular for deep learning due to its adaptive learning rate capabilities. We specify categorical cross-entropy as the loss function, which is appropriate for multi-class classification tasks like ours. Additionally, we track accuracy as a metric to evaluate our model's performance throughout training. Now let's move on to augmenting our training data using the image data generator. This class provides a variety of transformations to our images, such as rotation, width and height shifts, shear, zoom, and horizontal flips. These augmentations help create a more diverse training set, improving our model's ability to generalize and perform better in real-world scenarios. Following this, we use the flow-from-directory method to load our training data from a specified directory. This method will automatically label our images based on the subdirectory names, resize all images to 224 x 224 pixels, and set the batch size for training. By incorporating these steps into our workflow, we ensure our model is well prepared for effective training. Now let's proceed to the training phase of our model. Here, we will fit the model to our training data using the model fit method, which is crucial for teaching the model to recognize patterns. We specify the train generator as our input data, allowing the model to access augmented images during training. The steps per epoch argument determines how many batches of samples the model will see before completing one epoch, which is calculated by dividing the total number of samples by our batch size of 32. We will train the model for 10 epochs, a parameter you can adjust based on your dataset's complexity and size. It's also vital to include validation data through the validation data argument. This helps ensure that the model can generalize well to unseen data and prevents overfitting, as we will monitor the model's performance on this separate dataset. The validation steps argument indicates how many batches from the validation set will be used. Once this code executes, you'll receive output that tracks the model's performance across epochs, allowing you to identify any signs of overfitting or underfitting as training progresses. Now let's see how we can implement the fine-tuning process for our model by adjusting the training parameters and continuing the training phase. First, we set the trainable property of the base model to true. This change indicates that we want to unfreeze the Mobilenet layers, allowing them to update their weights during training, which is essential for adapting the model to our specific dataset. After unfreezing the layers, we recompile the model with a lower learning rate of 1e5. A lower learning rate is crucial here because it allows for smaller, more careful updates to the weights, helping to preserve the learned features from earlier training and avoid catastrophic forgetting. Next, we define the number of fine-tuning epochs and calculate the total training epochs, which includes both the initial training and the fine-tuning stages. Finally, we call the fit method again to continue training the model. This step involves using our training and validation generators to provide the model with data, allowing us to monitor its performance over the total epochs. By following this method, we ensure that both new and existing features are effectively adjusted to optimize our model for the unique characteristics of our dataset. Now let's evaluate the performance of our trained Mobilenet model on a test dataset. We start by setting up an image data generator, which is crucial for preprocessing the test images. By applying a rescaling factor of 1:255, we ensure that the pixel values are normalized to a range between 0 and 1, which is necessary for the model to interpret the input correctly. Next, we create a test data generator that flows images directly from the test dataset directory, specifying the target size to match the model's input requirements and defining the batch size and class mode. This allows for efficient loading of images in batches during evaluation. Then we utilize the model evaluate function to compute the loss and accuracy of the model on the test set. It's essential to monitor the accuracy, as it directly reflects how well the model generalizes to unseen data. Finally, we print out the test accuracy, giving us insights into the effectiveness of the model for real-world applications, highlighting areas such as misclassifications that can be further examined through confusion matrices. This evaluation step is critical in understanding the model's readiness for deployment. Now let's see how we can implement predictions with our trained Mobilenet model on new images. First, we'll import the necessary libraries from TensorFlow, specifically the image processing functions. Our goal here is to load and preprocess an unseen image that we want to classify using our model. We'll specify the path to the new image and use the loadImg function to resize it to the required input size of 224 pixels, which matches the dimensions expected by Mobilenet. After loading the image, we convert it into an array while normalizing the pixel values by dividing by 255, a common practice to rescale pixel values to a range of 0 to 1 for improved model performance. Next, we expand the dimensions of the array to prepare it for the model's input format, ensuring it has the shape 1, 224, 3. After preprocessing, we pass the image array through our model with the predict function, which outputs probabilities for each class. Finally, we find the predicted class index using NP-argmax, which identifies the class with the highest probability, allowing us to interpret the result of the inference. This streamlined process enables easy integration of image classification into your application or service. Now let's see how we can convert our trained model into TensorFlow Lite format for deployment on mobile devices. The first step involves using the TF Lite converter, which allows us to take our Keras model and prepare it for conversion. By calling the fromKeras model method with our trained model as an argument, we initialize the converter to handle the specifics of our model architecture. Following that, we invoke the convert method, which performs the actual transformation into the TensorFlow Lite model format. This process optimizes our model, resulting in a significantly smaller file size suitable for mobile applications, ensuring faster inference times and reduced memory usage. Finally, we will save the converted model to disk. This is accomplished with a simple file write operation, where we open a new file with the extension tflite and save our optimized model as a binary file. This converted model can now be loaded into mobile apps, providing efficient image recognition capabilities without sacrificing accuracy. Integrating this lightweight model into your application will help achieve responsive user experiences while efficiently utilizing device resources. In conclusion, we've traversed the landscape of retraining Mobilenets for image recognition. You learn not just how to fine-tune a pre-trained model, but also how to evaluate its performance, make predictions, and apply optimizations for mobile deployment. By combining the sophisticated capabilities of Mobilenets with TensorFlow, you're well on your way to developing powerful and efficient image recognition applications. As we embark on practical projects, you'll see just how dynamic and rewarding this journey can be. In June 2017, Google unleashed the full potential of Mobilenets, a series of models designed specifically for mobile devices. This revolutionary release included 16 mobile-first deep learning models optimized for TensorFlow, each catering to the need for efficient image recognition. Mobilenets offers an incredible blend of speed and accuracy, making them an excellent choice for mobile applications. So far, we learned about the architecture and efficiency of Mobilenets, particularly focusing on retraining for specific datasets using pre-trained models. We explored how to set up and compile the Mobilenet model in TensorFlow, including data augmentation techniques to improve model performance. The training process was discussed, covering how to monitor performance and fine-tune layers for better adaptation to the dataset. Finally, we emphasized the importance of evaluating model performance and applying optimization techniques for deployment in mobile applications. Now, we will talk about the efficient use of Mobilenets for fast image recognition and dive into some practical examples to illustrate their implementation. Now let's see how we can implement the initialization of our Mobilenet model in our Android application. The line of code we're looking at is key to setting up the TensorFlow Lite interpreter, which will allow us to run inference on our image data. In this snippet, we create an instance of the interpreter class, which provides a way to interact with our model. We pass the model file, in this case, Mobilenet tflite, to the load model file method. This custom method is vital because it handles the task of reading the model from the assets folder where it's stored. By doing so, we ensure that our application can access the pre-trained Mobilenet model, which has been specifically optimized for mobile devices. This initialization step is crucial as it establishes the foundation for the inference process. Once we have the model loaded into the interpreter, we can begin processing images either taken from the camera or selected from the gallery. From here, we will need to prepare our input images to fit the model's requirements, ensuring that they are properly formatted for accurate predictions. Now let's implement the following image preprocessing steps necessary for Mobilenets. We begin by reading the image from a file path using the bitmap factory class, which decodes the image into a bitmap object. This bitmap is the raw representation of the image that we will later scale and convert to the required format. Next, we resize this bitmap to 224 x 224 pixels, which is the expected input size for Mobilenets. The createScale bitmap method helps ensure that the aspect ratio is maintained for more accurate image representation during inference. After scaling the image, we create a 4D array named input to hold the normalized RGB values in a format compatible with the Mobilenet model. Then we loop through each pixel in the resized bitmap using nested for loops that iterate over the height and width dimensions. For each pixel, we retrieve its color value and separately obtain the red, green, and blue components. Each color channel value is then normalized by dividing by 255f, converting the pixel values from the 0 to 55 range into the 0, 1 range suitable for the model's input. This ensures that the neural network can effectively process the image data for accurate predictions during inference. Now let's see how we can interpret the output data from our Mobilenet model to determine the top prediction. First, we initialize a two-dimensional array called output to hold the probabilities for each class. This array is set up to contain a single batch of predictions corresponding to the different classes defined by num classes. Next, we run the model on our prepared input by invoking the run method of the interpreter, passing the input and the output array. This step executes the inference and fills the output array with the model's predicted probabilities for each class. To find the most likely class, we initialize top index to -1 and max confidence to 0f, which will help us track the index of the class with the highest probability as we iterate through the output. In the loop, we check each value in the output array. If a probability exceeds our current highest confidence, we update both max confidence and top index to reflect this new highest value. By the end of this loop, top index will contain the index of the class with the highest probability, allowing us to convey a meaningful prediction to users, such as identifying the image as a Labrador retriever with a specific confidence percentage. Now let's see how we can implement model quantization for the Mobilenet using TensorFlow. First, we start by creating a TF-like converter instance from the Keras model we previously built. This converter will allow us to convert the model into a form that is optimized for mobile devices. Next, we set the optimizations parameter of the converter to include default optimizations, which encompasses quantization. This step is crucial as quantization can help reduce the model's memory footprint and improve inference performance without significantly degrading accuracy. After defining the optimizations, we call the convert method to generate the quantized TF-Lite model, which will effectively prepare our Mobilenet for deployment on lightweight platforms such as mobile devices. Finally, we write this quantized model to a file named Mobilenet quantized tflight. This output file can be easily incorporated into mobile applications, enabling efficient image classification capabilities while utilizing reduced computational resources. By following these steps, you ensure that your Mobilenet model is both efficient and fast for practical use in real-time applications. Now let's see how we can implement performance measurement for our Mobilenet model during inference. To ensure that any optimizations applied do not negatively impact the model's performance, it's crucial to measure the inference time accurately. We accomplish this by starting a timer right before we execute the inference call and stopping it immediately afterward. In the code, we first capture the current time in nanoseconds before we invoke the run method on our TensorFlow Lite interpreter, passing in the input data and output placeholders. After the inference is completed, we capture the end time. By calculating the difference between the start and end times, we can determine how long the model took to process the input image and produce results. This performance metric is especially important in applications that require real-time processing, as it helps us verify that the model meets latency requirements. Lastly, we log the time taken to the console, which provides a clear insight into the model's efficiency in the context of image recognition tasks, allowing developers to make informed decisions for further optimization. As we dig deeper into deploying Mobilenets, let's consider integrating it within real-world scenarios. Mobilenets excel in environments with constrained resources, making them ideal for mobile apps that require real-time image recognition. Applications could range from augmented reality experiences to fitness apps detecting exercises through camera feeds. Imagine a fitness app that identifies whether users are performing squats or lunges. You can use Mobilenets to process frames from a camera feed and classify the moment in real time, providing instant feedback. The model can be trained using images of different exercises, leveraging techniques like transfer learning to adapt effectively to your specific dataset. Finally, let's discuss best practices. When implementing Mobilenets for your applications, ensure continuous evaluation and adjustment of the model based on user feedback and performance metrics. Mobilenets provide a robust foundation for image recognition, but the final application should always evolve based on real user interactions and demands. To sum up, efficient use of Mobilenets for fast image recognition involves understanding the architecture, implementing preprocessing techniques, optimizing the model for mobile use, and continually assessing performance. With these elements, you can create responsive, intelligent applications that leverage the power of deep learning on mobile devices. Whether you're building self-driving car applications or personal fitness trackers, Mobilenets are here to help push the boundaries of what's possible with image recognition on mobile platforms. In June 2017, Google made a significant contribution to the field of mobile computing by introducing Mobilenets v1, a set of 16 mobile-first deep learning models designed for TensorFlow. These models leverage depthwise separable convolutions, allowing for efficient image recognition tasks on mobile devices while keeping the computational requirements low. Now let's see how we can implement a Mobilenet model in our Android application using TensorFlow Lite. The code demonstrates the creation of a class named Mobilenet model, which is responsible for loading the Mobilenet model and making image classification possible. Initially, the model is instantiated by passing the model path to the constructor. Here, we utilize the loadModelFile method to read the model file and create a memory map byte buffer, which allows for efficient model loading. In the core functionality of this class, we define the classifyImage method, which takes a 2D float array as input. This input represents the features of the image we want to classify. The model processes this input data using TensorFlow Lite's interpreter, which runs inference on the input and fills the output array with probabilities corresponding to 1001 possible classes. This straightforward approach enables the integration of powerful image classification capabilities in applications, allowing developers to utilize the efficiency and optimized structure of Mobilenet for real-time image recognition tasks on mobile devices. Now let's see how we can retrain a Mobilenet model with quantization support to optimize its performance for mobile deployment. The command provided initiates the retraining process using TensorFlow's image retraining scripts. We begin by specifying the output graph flag, which indicates where the retrained model's graph will be saved. The output labels flag defines the location for the labels generated from the retraining process, which is essential for interpreting the model's predictions. The image_dir flag points to the directory containing sample images used for training, showcasing how the model can learn from different visual inputs. Next, the bottleneck_dir flag is set to store intermediate data that optimizes the retraining process by speeding up subsequent runs. Finally, the architecture flag is crucial as it specifies using the quantized version of Mobilenet. This quantization not only reduces the model's file size, but also facilitates its use on resource-constrained devices, ensuring efficient operation while maintaining an acceptable level of accuracy. Now let's implement the image preprocessing function, which is essential for preparing our input images for the Mobilenet model. In this method, we start by resizing the input bitmap image to the required dimensions of 224 x 224 pixels. This is crucial because Mobilenets expect input images to be in this specific size to ensure consistency during inference. Next, we retrieve the pixel values of the resized image and store them in an integer array. This allows us to access the RGB values of each pixel easily. We then create a two-dimensional float array to hold the normalized pixel values, properly formatted for the Mobilenet model. The conversion process involves extracting the red, green, and blue components from each pixel's integer representation. As we iterate through the pixel values, we perform normalization by dividing each color channel by 255, scaling the values to a range between 0 and 1. This step is vital for the model to process the input effectively, as it typically expects normalized values. By the end, this preprocessing method returns the properly formatted input array, ready for the Mobilenet model to make accurate predictions. Now let's take a look at how we can interpret the output from our Mobilenet model after making an image classification. The getPredictedLabel method is designed to analyze the output probabilities produced by the model, which essentially represent the confidence for each class label. The method begins by initializing maxIndex to track the index of the highest probability found and maxProb to store the maximum probability itself, starting with the first element of the output array. We then iterate through the probabilities starting from the second element, comparing each probability to maxProb. If a higher probability is found, we update both maxProb and maxIndex accordingly. This straightforward approach efficiently identifies the most likely class predicted by the Mobilenet model. Finally, once we've determined the index of the maximum probability, we format a user-friendly string to display the predicted class label alongside its associated probability. By encapsulating this functionality in a method, we provide an easy way to interpret and present the results of our image classification effectively, enhancing user experience and understanding of the model's predictions. Now let's take a look at how we can benchmark our Mobilenet model to assess its performance. The command begins with calling the benchmark model tool from the TensorFlow repository, which is essential for evaluating the efficacy of our model. The graph flag specifies the path to our optimized model file, ensuring that the benchmarking process is conducted on the correct iteration of our Mobilenet architecture. This is crucial for obtaining accurate performance metrics. We also define the input layer with the input layer option, specifying mul as the name of the operation representing the input tensor in our model. Furthermore, the input layer shape option is set to 12,992,993, indicating that our model expects an input size of 299 by 299 pixels with 3 color channels, which aligns with the input requirements for image classification tasks using Mobilenets. Next, we define the input layer type as float, which reflects that our model processes floating point data for improved accuracy. The output layer parameter identifies the final output of the model, helping us track the classification results. The flags show run order, show time, and show memory are set to false, meaning we are not interested in those specific details during this run. Instead, we enable a summary report with show summary equals true, which will provide us with a concise overview of our model's performance. This detailed report is invaluable for understanding how the model behaves in real-world scenarios. In conclusion, effectively using Mobilenet models for fast image recognition involves an understanding of their architecture, proper implementation strategies, preprocessing techniques, and ways to interpret outputs. As the demand for mobile applications continues to rise, leveraging efficient models like Mobilenets is key to developing swift, responsive applications. By mastering the deployment of these models, you will enhance user experiences, ensuring your applications are not just functional, but also maintaining high performance. Remember, with great power comes great responsibility. Keep evaluating and refining your models for the best results. In the world of deep learning, efficiency and speed have become crucial, especially for mobile devices. In June 2017, Google released Mobilenets v1, a set of 16 mobile-first deep learning models optimized for TensorFlow, striking a balance between accuracy and computational efficiency. Today, we're going to dive into how you can use Mobilenet models to achieve fast inference speed, crucial for mobile applications where resources are limited. So far, we learned about Mobilenets, a set of efficient deep learning models designed for mobile devices that utilize depthwise separable convolutions. We explored their implementation in Android applications, focusing on model initialization, image preprocessing, and output interpretation. Techniques like quantization were discussed to enhance performance while minimizing resource usage. Lastly, we emphasized the importance of continuous evaluation and refinement of models to ensure accurate predictions in real-world applications. Now, we will discuss efficient strategies for using Mobilenet models to maximize speed without sacrificing too much accuracy. Now let's implement the following code snippet to initialize and run our Mobilenet model using TensorFlow Lite in an Android application. We begin by loading the pre-trained Mobilenet model using the interpreter class, which is essential for executing inference efficiently on mobile devices. The model file, Mobilenet tflight, needs to be loaded for the interpreter to utilize it properly. Next, we prepare our input tensor, which is a 4-dimensional array suitable for Mobilenet's input shape. This array should represent an input image, ensuring that it is pre-processed into a normalized float format of size 1x224x224x3. This normalization is crucial for proper inference as it aligns the data with the expectations of the model. After setting up the input tensor, we also define the output tensor to capture the predictions. Consisting of another array of size 1x1001, this tensor holds the confidence scores for each of the 1001 classes supported by Mobilenet. We then invoke the run method of the interpreter, passing in our prepared input and output tensors. This method executes the inference and populates the output with predictions. Finally, we utilize the getMaxIndex helper function to determine the class index corresponding to the highest confidence score, allowing us to extract the most likely prediction based on the model's output. Now let's see how we can implement quantization during the model conversion to TensorFlow Lite, which is essential for optimizing Mobilenets for mobile applications. We begin by importing the TensorFlow library and loading the pre-trained Mobilenet v2 model that is designed for image classification. This model utilizes weights learned from the ImageNet dataset, ensuring a high level of accuracy. Next, we set up the TensorFlow Lite converter that will facilitate the conversion process. By assigning the optimization option for size reduction, we instruct TensorFlow to apply quantization automatically. This process converts the model's weights and biases from floating point values to lower precision formats like int8, resulting in a significant decrease in model size without compromising much on accuracy. After configuring the converter, we call the convert method to create the quantized TensorFlow Lite model. Finally, we save this optimized model to a file with a tflight extension, which can be loaded on mobile devices. This quantized model is crucial for enabling faster inference speeds, thus enhancing the efficiency of applications built on constrained mobile hardware. Now let's implement the image preprocessing needed for our Mobilenet model in an Android application. The method begins by resizing the input image to a standard dimension of 224 by 224 pixels, which is crucial because Mobilenet requires this specific input size for optimal performance. This resizing ensures that no matter the original dimensions of the bitmap, it will be converted to the expected format before further processing. Following the resizing, we initialize a four-dimensional array to hold the preprocessed pixel data for each color channel. This array structure corresponds to the model's expectations, as it follows the format of 1/224/224/3, where 1 represents the batch size, and the last dimension contains the RGB color channels. As we loop through each pixel of the resized bitmap, we extract the individual RGB components and normalize them to a range of -1, 1. This normalization is a critical step because it allows the neural network to interpret the values correctly, facilitating better learning and inference performance. Each channel is first divided by 255 to convert it from an integer value to a float, then adjusted by subtracting 0.5 and multiplying by 2. This careful manipulation transforms the pixel values into the range expected by the model. Finally, the method returns the processed image ready for inference. Now let's see how we can retrain a Mobilenet model using TensorFlow's Retrain script. This command initiates the retraining process by specifying the output for the new model and labels, directing the script to the folder containing the images for training. The output graph flag specifies where to save the retrained model, while the output labels flag saves the corresponding labels for the model's outputs. Next, the image dir option points to the location of your input images, ensuring the model has the necessary data to learn from. The bottleneck dir flag is crucial as it indicates where to store bottleneck files, which speed up the retraining process by caching intermediate results from previous runs. Finally, the architecture flag allows you to select a specific variant of Mobilenet that best balances accuracy and speed based on the needs of your application. Once you run this command, TensorFlow will start the retraining process, enabling the model to be fine-tuned for your specific dataset, allowing for enhanced performance in tasks like object detection. Next, we will implement a simple performance logging mechanism around our model's inference call to monitor the time taken for predictions. We start by capturing the current system time just before invoking the run method on the TensorFlow Lite interpreter. This is accomplished using system current time millis, which retrieves the current time in milliseconds since the epoch. Now let's see how we can track the model's performance by executing the inference with the provided input and output tensors. After the model finishes processing the data, we again capture the current time. By subtracting the start time from the end time, we can determine how long the inference took. This metric is crucial, as it allows us to analyze the speed of the model and identify any potential bottlenecks. Finally, we log this inference time to the console using logd, which enables us to view the results during our debugging sessions. By implementing this code, we gain valuable insights into our model's performance, allowing us to make informed adjustments for optimization based on the recorded inference times. In conclusion, the Mobilenet family of models opens new avenues for deploying deep learning applications on resource-constrained devices effectively. Their architecture optimizes for low latency and high speed, crucial for mobile applications. Through techniques like quantization, effective preprocessing, and model retraining, we can significantly enhance the performance of our applications. The efficient use of Mobilenets not only aids in achieving faster inference speeds, but also allows developers to create more responsive mobile applications that align with user expectations. In this session, we've covered the efficient use of Mobilenet models for fast inference speed. Now you possess the knowledge to implement Mobilenet effectively, enhance your model's performance through quantization, and optimize your applications on the go. As you dive deeper into your TensorFlow applications, keep refining and testing your models to unlock their full potential. In this final section, we will do a project challenge to apply what we have learned so far. The objective of this project is to develop a mobile application using TensorFlow that showcases your understanding of machine learning concepts. You will have the freedom to choose from 3 application types. Create an image classification app that uses a pre-trained model to identify objects in photos. Build a stock price prediction app employing RNN or LSTM techniques to forecast market trends, or design a game-playing app that leverages reinforcement learning to challenge users. Throughout the project, you will set up your development environment, gather and pre-process datasets, build and train your models, implement an intuitive user interface, and rigorously test your application for optimization. Document your journey, detailing challenges faced and solutions developed, then present your application to showcase its features and performance. This is an excellent opportunity for you to innovate and apply your skills creatively. Remember, the final project details are available in the GitHub repository linked in the description.